So hello and welcome to the fourth day of the LPC. I can hear an echo.
We can hear a bit of your echo as well. Oh, I have echo too. Wow, it must be universal. That sucks. Can you say something, Daniel, again?
Let me see if I.
No, I think you fixed it. I think that you were the cause of the echo. Oh, well, Lauren's saying it's good. Okay, perfect. So I'm assuming Brian's won't have this issue.
Can you hear me well?
Yep.
Okay.
Yeah, we can hear. Let me see if it works now. Yeah, so let me quickly kick off the today's session with thanking the sponsors. I'd like to thank Facebook, IBM, and Microsoft. Silver sponsors AWS, Netflix, and Red Hat. Collabora for the speaker gift. And last but not least, the t-shirts from VMware. And general conference services from the Linux Foundation. And as usual, the housekeeping, in case you would like to comment, have questions, feedback to the speaker, please unmute yourself and turn the camera on. And yeah, last but not least, thanks to all the hard work that the LPC committee put into this conference. And yeah, without further ado, I'll now switch to Brian's talk and finally mute myself. So hello, Brian, and yeah, please kick it off. Thanks.
Sorry, are you going to switch the presentation or? Okay. Okay, I'll start. So hi everyone. I'll start introducing myself. So my name is Brian Vasquez. I'm a software engineer at Google and I work in the kernel networking team. And today I'm going to talk about how to do dynamic encapsulation using BPF. So let's get started. This is the agenda for today. First, I'll talk about the motivation and how this dynamic encapsulation was first implemented in the kernel, then how we BPFI the solution, and also I'm going to talk about how we extended the BPF solution to do encapsulation header reflection. And during the talk, I'll introduce some challenges that we faced. To make more interactive, and feel free to interrupt and ask any question at any time. So let's get started. So the motivation. So motivation was to do traffic engineering, and the goal was, or the requirement was to forward traffic via specific routes. And the main point here is that these routes could change in the middle of a connection. And this was like really long time ago. So I also want to point out that when this started, like it was prior to lightweight tunnels. So the only approach at that time to having these special routes to direct traffic was setting up multiple tunnel devices. And the problem is that doing traffic engineering using tunnel devices require root permission and configuring hundreds of devices that would have impacted the performance of the system. So we wanted to design an application or a feature in the kernel, and we wanted to achieve these three goals. So the first one was to allow unprivileged applications to pick the exit point without having to create tunnel devices, and this was to cover the performance issue. And when I said unprivileged application, it's not really that they are unprivileged, but so we do have some per C group level control. But the idea is that once we have a host, we don't want users to change the configuration. We want to know what it is at every point in the time. So that was the reason. The other requirement was to allow each connection to be encapsulated to a different destination. And this was the initial requirement, but later we also extended to change different protocols as well. And the third requirement was to allow the exit point to change in the middle of a connection. So now let's move to how it was implemented in the kernel. So this was also before BPF was popular and was that powerful. So just to keep that in mind. And the way that we implemented it, it was using internal patches that we apply on top of the IP tunnel device. And what we did was to add a per socket state, where basically we indicated what were the destination gateway, or we kind of cheat and change the protocol headers for the encapsulation in case we needed it. And the way users populated this information was using set socket options at the IP level. And so basically that was how we populated this per socket state. And we started with only one set socket option that we created internally, that it was encap gateway, but later we exchanged it to do different encapsulation headers. So this is only like historical reason why we have two set sockets instead of one. And we keep that implementation. So now that I talk a little bit how it was implemented, I also want to talk about the host configuration, because it's also important. Because as soon as we started to add these encapsulation headers and change and use different protocols, the length of the packets change depending on what the application is using at that specific point in time. So what we wanted to do is we want to do MSS clamping or MTU clamping to make sure that the packets are going to fit the MTU before they leave the host and after the encapsulation headers are added. So how we did it, we used basically a special mark to distinguish the standard routing table and the special routing. So we could force this special traffic to leave the host using a different device and different table and different routes. So here I have an example of basically one of the rules that that I use just to explain this point. So we are setting that all the packets that are set with this mark will go to table 1000, and this table 1000 is using this tunnel device where we apply the logic to it, and basically we are clamping the MTU and the MSS. And here are little explanations, but this is just an example, and it's just to show you what you need to consider when doing this. And so now that you have an idea of how it was done in kernel, I want to introduce the first challenge, because this challenge is not only for the kernel, but it's also present in the BPF implementation, and is that when we change the routing based on certain actions, for example, we can set the mark or the toss for a socket, and this could cause different routing policies, right? So as I told you, one of the requirements for this dynamic encapsulation was that the connection can change in the middle. So this means that we need different MSS, and the problem is that the MSS is cached. So basically packets can be malformed because of this, and this was solved with an internal patch that I have plans to send upstream. And basically the idea is that during these set socket options, the ones that could cause the routing policies to change, we plan to call also this function, which basically resets the DST and also like reveals the header and also tries to update the MTU in case of the new route is using a different MTU. So now let's talk about how we implemented this solution in BPF. And I'm assuming that all of you are familiar with BPF, so you all know what are the benefits of doing this in BPF. But still, I will mention that we wanted to get rid of these custom patches that we have in the kernel, and that were clearly not candidates for upstream work. So of course, we went and implemented this in BPF. Before I dive into how we did it, I want to compare two different solutions because in BPF we have two different hooks, the lightweight tunnels and the TC hook. And I just want to make some quick comparison between them. And the first one is that lightweight tunnels attaches to routers and TC attaches to QDISC. And this is important because these two hooks are in two different parts of the networking stack, which means that you don't have the same access depending on which one you decide to run, and you are restricted. So basically, it was important for the decision we made. And another point is that both run before software segmentation. And I know that this point is not clear right now, but I explain later why it matters. And as I stated before, lightweight tunnels was more restricted in terms of reading and writing fields and BPF helpers. And also some features, for example, lightweight tunnels don't have access to SK local storage. So I'm not saying that lightweight tunnels could have been used if, of course, it would mean more work for us. So we decided to use TC based on available BPF helpers, and because we already have programs running in the TC hook, and for us it was easier to extend those programs and take advantage of the current infrastructure. So now let's move about how it was designed. And it was pretty similar to the kernel implementation. So we have a socket data that lucky us, we have the local storage map available. So all the handling, it's transparently done for us. And what we store in this data, in this map, sorry, is the encapsulation data. So I'm mentioning here just the BPF destination. But you can, I'm not showing this structure here, but you can think of this structure as basically a way to write certain IP router headers information like destination or source address. And also you can include the encapsulation headers, for example, UDP, if you want to do some custom encapsulation, so not necessarily GRE. And the idea of the design was to have similar implementation to the previous, to the kernel dealing cap that we did. So it was straightforward to do in the sense that we already used these setsock options that I told you before. And what we are doing is capturing these setsock op calls and storing the encapsulation headers that the user is providing us and store it in the SK local storage. So here's an example of how we are changing the destination. So basically we are creating the local storage. We are copying the op value, which for this example contains a new destination address. And it's still important that we distinguish these packets that are being encapsulated. So we set a special mark. And also important to note is that when we switch to this implementation, actually the setsock option that we are capturing doesn't exist in kernel. So that's why we are returning -1, because we are bypassing the kernel. We don't want this call to go to the kernel. And so this was one part of the problem, which is the control path, and the other one is the data path. And the data path is basically where we read the encapsulation data at the TC Grace hook, and we modify the packet. So I'm just showing you here how more or less the code should look like, but it's just an example. So what we are doing is we are just reading the local storage, and we are loading certain information from the packet so we can reuse some of it. And we are also adding the room for the encapsulation headers, and we are storing it. So basically, this is how it was done. And here I want to stop and also explain something that it was a goal when we moved to eBPF. And it was that we wanted to do this without a tunnel device. And actually, it worked pretty well until we discovered the next challenge. And the next challenge is that neither TSO or GSO understand custom or multiple levels of encapsulation. And the problem is that packets need to feed the MTU after encapsulation headers are added. And the real issue here was that we don't have in BPF TC hooks that run after software segmentation. So what happened is that we were adding encapsulation headers here, but there wasn't a way where GSO could understand this. So the way we fixed it was not straightforward, and it was interesting. So we ended up adding back the tunnel device. And we added the tunnel device back because by disabling the TSO in the tunnel device, we can force the packet will traverse the network stack twice. So we can force the first time to execute the software segmentation. And then we attach in the physical interface the next hook to modify the headers. And this is a little bit tricky because what this means is that the packet that we modified, it's already being encapsulated. So you just need to be careful on how you do it, because you need to change the protocol or you need to add certain room, but you need to consider that it already had some kind of encapsulation. And so now that you have an idea of how this was done in BPF, I want to talk about a feature that it was interesting as well, and it's reflection. So what's reflection? In the past, we have implemented different reflection features. For example, one of is the TOS reflection. And I'll talk a little bit for the TOS reflection. So the idea here is that the client has certain TOS when it sends the same packet to the server, and the server should reply back with the same TOS. So it maintains the same quality service. So here the idea is pretty similar, and thanks to eBPF doing it was actually possible. So the objective was the same, like as part of the traffic engineering, sometimes packets need to traverse along the same path. And these packets sometimes need additional metadata, and it could be, for example, a virtual network ID. And something important is that most of the times this encap data is not relevant for the application that is serving the traffic. So they don't need to be aware of this overlay network or these encapsulation headers. So how we do it, how we extended DNCap to add this reflection feature. So it was still using the DNCap, so we could reuse it completely. And the difference is how we populate the BPF map, which is the SK local storage. So basically, we were using set sock-up option, so users could specify the encapsulation headers. But for reflection, we want to store the data for incoming connections. So what we did here is to use the cgroup SKB ingress hook, and that was where we captured the data. So to give you an idea, this is how it looks like. This is a program that we are running to the SKB ingress, and what we are doing is we are loading the bytes, but we want to start at the MAC header, because when the cgroup ingress hook runs when the packet has already made it to the socket. So this means that the first encapsulation header was removed, and it was able to be receiving the application. So here, basically, we load at the MAC to get the encapsulation header that was removed, because we still have it in the SKB. And basically, what we use is to try to compare the length of the outer header, that it could be an inner header, and based on that, we know if the packet was encapsulated or not, and we store the data in the local storage. So this is more or less also an example of how we store the data. In this case, I'm just storing the destination and source address in the SK local storage, which is dest, but for sure we put it dd, so that's fine. And everything worked well, but also there was another challenge that it was not obvious, and we missed it in the original design. So the next challenge is basically that SK storage is not available for listener sockets because you are working with the request socket, which is a lightweight version. So this actually was an interesting problem, because what this means is that the first assumption that we did that we could handle this more or less transparently didn't work for just the SIM packet, which was unfortunate. So how we solved this, we had to add a global BPF map, which is not the SK local storage. So we have a different map, and we use the file tuple as a key. So we consider source, destination, and ports and protocol to store the encapsulation header for that protocol. And as soon as the connection is established, we basically move that entry to the SK local storage, and we remove it for the global map. So of course, the global map is temporary. So we decided to use the LRU hash. And something important to mention here is that we also wanted to isolate this global map, because in case that we have a SIM flood, we don't want to compromise all the applications that are using encapsulation headers reflection. So we isolate this map, and we are loading this map per C group. So each user has its own view. So if there's a SIM flood, only one user is compromised. So this is more or less the problem. This was actually really interesting, and I'm actually really curious if someone in the community has faced similar issues with the socket storage, and how to solve it, or how it was solved in your case. And now I'm basically going to the last part of the presentation. So I'm going to talk a little bit about what were the conclusions. And the first one is that BP engine and CAF solved the goals that were initially set. So this was really nice. And the reflection features that came after, it was a requirement that it was also easily extended in some sense, except just for the inconvenience of the local storage. So again, BPF is powerful and it's nice, and this allows us to move this logic that was quite complex, and it was invasive, because we have this feature in some sense similar, and it was implemented in the kernel. So that was nice. And what went wrong? It's not really that it went wrong, but it was surprising. And so basically modifying packets in the middle of the connection uncover unexpected issues, like the MSS that is cached, or the fact that if you want to do custom encapsulation headers or multiple layers, you still need to go to GSO, and GSO doesn't understand that. So we need to add it like an extra device just to work around that. And the local storage issue was as well. And also in general, I would say that BPF is really nice and it's powerful, but it's also quite complex, because in each hook, you need to basically know in which part of the stack it is, and what you have access to, and what are the expectations. And also I want to conclude with some nice to have that would make our life much easier when we were doing this. And the first one is SK local storage for listener sockets. I'm aware that this is not done because the local storage needs a lock, and the request socket doesn't use a lock, but could we have like some light version of it, or would it be possible? The next point is a tunnel device. Could we have like a tunnel device that doesn't add headers? So it's more like in a programmatic way, it allows you to do whatever you want, and it avoids the issue of GSO. And this one probably wasn't obvious, because we changed the implementation from not having tunnels to adding a tunnel device, but basically, when you don't have a tunnel device and you want to modify the packet, you want to add the source IP. And the source IP usually is a device that is in certain namespace. So this data is per namespace. And there are a lot of configurations where we have namespaces and multiple C groups, multiple applications with different C groups are using the same namespace. So I think that it would be really useful at some point to maybe have a namespace storage. And last but not least, I want to thank to my coworkers who were key contributors of this work. So thanks Coco, Mahesh, Stan, and Willem for contributing in this project as well. Thank you for listening. And with this, I hit the end of the talk. So I'm ready for open discussions or any question that you may have.
Thanks a lot for your talk, Brian. And hopefully my echo is also fixed. Does anyone have questions or feedback or similar issues that you faced and solved it differently, for example?
So just regarding the local storage for the listener socket, Martin is an expert here, so I think he's trying to connect. He's saying actually that listener socket is a full socket, so it should, like, if it doesn't work, there is a bug, so it should be available. Like on a request socket, not, but listener socket's supposed to be the full sock, so maybe it's just like extra. Yeah, I'm not sure what went wrong there, like in where you have this pointer to a socket that it doesn't have it. So we probably should debug it offline, but it should work. But I will let Martin comment.
If I recall correctly, the problem is with the first SIM packet, because the first SIM packet only has access to the request socket. So that doesn't have the SK local storage available. So we need this global map and this workaround only to reply for the CNAC.
I had another question. So maybe, I mean, if Martin is connecting later and he has a comment, we can just jump in. I had a question regarding this dummy tunnel device. Do you see ways where we could achieve the same without having an extra device that we would need to allocate just for this? I mean, I would assume maybe like on a node, there are different use cases, different, or potentially encapsulation with different header lengths or so. So you probably don't want to add several tunnel devices that you would need for this. Do you see options where we could, or like where BPF could just encode this into the SKB, for example?
So also, like if I recall correctly, there are certain flags that that could be used for this GSO in the BPF helpers, but still I think that they don't understand, for example, if you have multiple layers of encapsulation. So imagine that you have GRE with multiple MPLS labels. So this is where it gets tricky. And yes, probably I need to look more into this problem. And yes, it could be maybe solved without a dummy device. This was unfortunately, we discovered this issue like pretty late in the development process. So we just find how to work around it as soon as possible. And it was adding this device to have the software segmentation. But yes, it could be interesting if this could be done without the tunnel device.
Yes, sir. Related to that, we basically disable GSO and TSO It would be ideal if we don't have to do that, if we can rely on something like GSL partial to just pass these packets regardless of headers to the NIC. But another issue is that this BPF program runs before segmentation, also before the QDisc. So other programs that do accounting of bytes on the wire also have the issue that if you run it in a BPF program before the QDisc, there might be drops that are incorrectly not accounted. So the other option would be essentially a BPF hook after this processing, after QDisc layer, after validate SKB XMIT, validate XMIT SKB. And essentially what we do by introducing a dummy device, because we don't really use the tunnel device as a tunnel, is to get that extra BPF hook. I assume that the accounting problem has come up for others as well, where you kind of misaccount packets and bytes on the wire if you do accounting in BPF on a device.
Okay, I see Martin raised his hand, so please pick up.
Yes, can you guys hear me?
Yeah, we can hear you.
Yeah, I try to start my cam, but it doesn't work, so yeah. So is it something that I can answer, or sorry, John 8?
Yes, so there was basically a question regarding the local storage that was implemented for sockets, and it's that basically when you have a TCP connection and you are receiving the first SYN packet for an incoming connection, you are working with that request socket. So the request socket, if I recall correctly, doesn't have, for example, a lock that was required for the SK local storage. So my understanding, and I believe that we tried it in the implementation, is that for this initial SYN packet, there's no way that we can use SK local storage. So I don't know if you have like comments on that, and maybe you've seen this problem or have ideas of how to work around it, or if it would be possible to extend the SK local storage.
Right. No, yeah, you're right. The local storage is not available to the request socket, right? So right now it's only implemented for all full socket like TCP socket, UDP socket, or listening socket, but not the mini socket like request socket. Why it's not there? Because I don't have a use case for that. It's nothing that we cannot add to it. Like I don't have a use case. It's like the request socket is like it's not like a permanent socket, right? When a full established socket is created, the request socket pretty much will be gone, right? So the use case is our current use case is like store something in the socket there, and then use it for a long time. So request socket just doesn't fit the use case that we have. But I can imagine that a case may come up like you want to save something in the request socket because, for example, you learn something from the same packet, I guess. You learn something from the same packet and then you want to store something there. Yeah, that makes sense. But somehow, so far, we get around it by saving the whole SYN packet per se, and then there's a socket option called save sync. Something says like save sync, right? There's a socket option to do that. So we save the whole SYN packet, and then later when the whole socket established, then we learn from the SYN packet that we saved it. Is it your use case that you want to save something from the SYN packet? That's why you want to create a local storage in the request socket?
Yes, so the idea of this work is that we want the SYN packet comes with encapsulation headers. So what we wanted to do is to add these encapsulation headers in this request socket or SK local storage, and we wanted to reply back and use the same information that we store. So we add the encapsulation headers back, but we wanted to do it in a way that the user doesn't need to interact with it. So the user wouldn't call to this save SYNAC or wouldn't set this metadata when it's established. We wanted to do it in a transparent way for the application. So we ended up like using a global map to store this temporal state, and once the connection is established, we detect that and we move just the entry from this global map to the SK local storage. So I guess that the suggestion or the approach that you were suggesting, it's pretty similar to what we did, just that we did it inside the BPF and without like calling the setsock options, but by using this global map.
Yeah, right now we save it. Right now we don't require the user to call setsock op also. We do it in the BPF program. So we enforce the save sync setsock op. So that's how we do it without asking the user application to call setsock op. The BPF program itself calls setsock op. But how do you guys solve the oh, but you saved it. Okay, nothing. I was just thinking the sync cookie, but yeah, that's fine. If you saved it in the BPF map, then yeah, then sync cookie will work too. Yeah. But even if you save it in the request, create a local storage in the request socket, then maybe you guys don't have the sync cookie case, so you guys don't enable the sync cookie of sysctl. Because in sync cookie mode, there won't be a request socket created in the server, right?
Yeah, I forgot if we were doing the sync cookie or how or when we enable it. But yes, like it's an interesting approach as well. So I look also into this BPF helper to see if I can use this to save the sync packet as well and how to recycle that information.
Yeah.
So I can see that Eric and also Jacob raised his hands. I presume Eric might want to comment on your previous reply from Martin potentially. So let's if you could unmute yourself first, Eric, and then afterwards Jacob.
Yeah, I am unmuted. So yeah, I just wanted to remind that under SynFloat we don't have a request socket, so I'm not sure we can extend the request socket to add a local storage because SynFloats are not that uncommon, even on hosts which are protected, you know, in the data center. It's not something that you can rely. There is no way you can have a full communication without any sync cookie ever. So it's whatever you come up, you need to have a solution coping with the sync cookie mode as well. So better just do it from the beginning. Also, I want to point out that under SynFloat, if we are really storing stuff in some map, that's going to be a scalability issue and a performance issue as well.
Okay,
All
so
right.
let's, yeah, Jacob, please go.
Yeah, thank you. So I was just wondering if I understood correctly, with your BPF setsock program, you've managed to build a replacement for SO mark effectively that doesn't require the process to run with CapNet admin. Is that right?
So something that I didn't show up in this presentation is that we also have permissions check at the C group level. So we are also implementing these special capabilities for these special features, and those are also in BPF. So basically, when a task is created, we populate these BPF fields as well to control what an user can or can't use.
I see, but that sounds finer grained than cabinet admin. Yeah, that's a really cool solution. Thanks.
So there was one more question, but I think you probably answered it from the chat from Lawrence. Since you mentioned the first SYN, does your scheme work with SYN cookies? If I recall correctly, you don't get the request sock for initial SYN. Yeah.
Yeah, so at the end, we ended up like using this global map. So we are actually not working at the request socket level. And also, as Eric mentioned, one of the problems that we have using this approach is that under a SYN flood, you basically you need to be mindful of your resources. So that's why we ended up like having this LRU hash map. So basically, yes, if we are under a SYN flood, of course we are going to recycle this hash table, and of course it's not going to work properly, but at least we are not using more resources than the ones that we are willing to give. And also because of this issue, what we do is we load different BPF maps, so each application has a different view and a different LRU map. So if an user is under a SYN flood, that doesn't affect separate users that is using this feature as well.
Okay, and one more comment from John. XCPTX more or less would be useful for us to do accounting and collect NetDev stats. Looks like a similar use case. Okay, does anyone have any other questions for Brian? If not, then thanks a lot. Thanks a lot for this interesting talk. And now we're having a short 10-minute break, and then at 7:50 Pacific time, we continue with the next talk. Thanks.
Thank you.
All right, so next up is Jacob and Arthur from Cloudflare presenting on BPF user experience rough edges. Let me shortly make you the presenter, and there you go.
All right, thank you. Right, hi everyone. I hope you can hear and see me well. It's super nice to be presenting again here at Plumbers. Thank you for having us. I'm Jakub. I'm a systems engineer at Cloudflare. And together with my colleague Arthur, we are going to talk today about rough edges and BPF user experience. So our agenda for today is straightforward. First, I'm going to go over what kind of problems we human developers can run into when developing BPF-based apps. And then Arthur is going to take us on a tour what can go wrong when machines are generating BPF code. First, though, a short disclaimer. Please don't take this talk the wrong way. We think that BPF is great. It allowed us to build projects that wouldn't be possible without it. And we know that years of hard work went into getting the technology to this place. So this talk is not about looking down on the problems, on the solutions, but rather to share the know-how, because if we've run into some issues, it's likely that other users will run into them as well. And also to trigger discussion about them. Maybe some of these problems can be smoothed out without too much effort. And finally, to show where help is needed because someone actually needs to do the work. All right, so here's our story. Meet our novice developer, Buzz. And Buzz would like to build an application like nStat that counts the packets going into and out of a host. But instead, Buzz would like an nStat that works per C group because services are usually restricted to their own C group. So that little project is going to be our benchmark for user experience. And we're going to have to go through a bunch of steps to prototype it. Being adult and all, anytime we run into problems, we're going to mark it with a set panda. Before we start, our test environments will be Debian Bullseye supporting an LTS kernel, as well as Fedora 34 that follows the stable kernel 5.13 at the moment. We'll need one more thing to make the slides readable, a small helper that will allow us to change the user and raise our capabilities easily. So anytime you see run as, just think of the command as being run under a certain user with certain capabilities. And if you speak the systemd lingo, that is similar to running your service with user group and caps set. Right, let's go. First step, first thing we need to do, we need to create a BPF map. Why do we need a BPF map? Well, we need to count the packets. So let's create a really small map with just one entry with a 64-bit counter in it. We built our user space application, try to run it, and we're actually not permitted to create a map. And that's kind of expected these days. Distros by default disable unprivileged BPF. And to actually get anything done, you need to at least cap BPF for your process. So, all right, we're just prototyping. Let's use sudo. Well, it turns out not so easy. And now to find out what's happening, we'll have to look under the hood, so to say. And with ftrace help, look what's happening in the BPF syscall. And we see that we get as far as BPF map charge in it. What happens there in LTS kernels, just before we start the teardown, we see that we check our allocations against the locked memory limit. So question is, are we hitting that? Well, first we need to know what actually the limit is set to. And the default differs from distro to distro, but it's we can check it pretty easily. A harder question, though, is what is the current usage? I mean, we need to know that if we are over the limit. And here we'll have to resort to some more tracing to actually dig out the current usage from the current task object down to the user that owns that task. And in this case, yeah, that's it. We are slightly over the limit. But why are we over the limit, though? We haven't created anything yet. Well, it turns out that the allocations are tracked by, per user, but you get a false sense that the limit is set per task. And what is more, the quota there is shared between all the maps, but also between the XDP sockets, IOU-ring, network applications that use zero copy, and perf, as long as they are running under the same user. So that's a bit confusing. Right, what's the solution for that? Well, we can just remove the limit completely and trust our application. And that is what BPF tool map create does. If we follow that approach, yeah, we can create the map, no problems. But if we want to still restrict our application, perhaps there's a better solution. And turns out we can use just a dedicated user for our BPF program. Because if we use a fresh user boss for our project and check the current locked memory usage, well, we start at 0 as expected. So there we go. We created a BPF map. We need to use a dedicated user and kept BPF to do it. Just a quick note that things have changed since 5.11, and now map allocations are charged against memory cgroup limit. Right, we have a place to count our packets. Now we gotta load the program that will actually do it. So here's our program. It's pretty straightforward. It gets a pointer to an entry in the map, and it will just bump the counter every time a packet comes into one of the processes in a C group. We build it, we try to load it, and we get an error that is really strange. I don't know what's going on here. And I know it's not memlog because I've done this test on 5.13. So if we trace it, it doesn't get any more clearer. I mean, it looks like the BPF syscall is not supported, which is not the case. So once again, we gotta go deeper and ftrace what is going on. This time the output is much longer, but if we follow through, we can see that we get as far as something called BPF JIT charged mod mem before all the teardown happens and we start freeing objects. And what happens in BPF JIT charge mod mem, we check if we are not over the BPF JIT memory limit. So maybe that's that. But what is the limit set to? Well, we have sysctl to check that. And in this case, I've artificially lowered this limit to 1 megabyte. The default is much higher. Once we know what the limit is, we need to know what the current usage is. And here, unfortunately, it's not exposed anywhere. We have to turn to tracing again to dig out the value of a kernel global. And yeah, we are over the limit. But why are we over the limit? Well, here's what I done for this test. I just added a bunch of IP tables rules that use BPF match extension. So what do IP tables rules have to do with our BPF JIT programs? Well, it turns out that all kinds of BPF programs are charged against the JIT memory limit. That includes the programs you load, as usual with BPF syscall, as well as seccomp programs, which automatically get translated from CBPF to BPF, and the IP tables rules that use the BPF match extension, sorry. What is perhaps more scary is that the limit is not per network namespace. But let's assume we've bumped the limit and managed to load our program. Now we need to create a BPF link for it. Why do we need a BPF link? Well, to attach our program to C group. We would like to attach it, but not the old way, where a BPF program is attached directly to C group This is what BPF cgroup attach uses, because that's a discouraged practice. You can end up with an abandoned BPF program. Well, perhaps that applies more to trace points, but nevertheless, newer types of programs don't even support this way of attaching. So we're going to go with BPF link. What is a BPF link? Well, it's an object that holds a ref to a BPF program and knows to which entity this program is being attached, being the cgroup, a network namespace, or a trace point. User space gets a file descriptor as a handle to our link. And the idea is that once the last file descriptor for the link gets closed, the program gets automatically detached and destroyed if there are no more references to it. So we want to create a BPF link, but here's the problem. BPF tool won't help us there. We gotta write a custom tool to do it. It's not super difficult, but that's a bump in the road for the user. But let's assume we've written our tool, we've loaded the program, we've attached it, and now we want it to keep it running, so we need to pin it somewhere so it persists. And the first question we face, where do we pin it? Well, the default BPFFS instance that we have mounted on our machines is actually only accessible to root, and that's because that's how systemd sets it up. And my colleague Lawrence asked about it on the mailing list, and the guidance on best practice that we received was that we should have a BPFFS instance dedicated for your service or your user. So let's just try to do that and mount an BPFFS for our user bus. Well, if we attempt that, we'll find out that the initial owner of the FS is not right, because it seems the BPF file system doesn't understand the options that allow you to set the initial ownership like TempFS does. But that's not a huge issue. We can just adjust it with change on, right? Except if you're using systemd mounts, then systemd doesn't allow you to change the ownership after mounting a file system, and it turns into a little bit of a mess. But we've done it, we've set everything up. Our program is attached. Now let's see how we can inspect the attached program. Why would we want to inspect the attached program? Well, perhaps we want to find out which maps it is using, or maybe read some of the program info, like its tag, to check if the correct version is loaded. With BPF tool, we can inspect the attached link, and we can see which program the link references, in this case, program ID 256. But if we try to inspect the program by the ID we found, that wouldn't be permitted for us. And here the troubleshooting is quite easy. We just got to look what BPF Pro get FD by ID is doing, and we quickly find out that unfortunately it's limited to users running with capsys admin. All right, that's fine. Let's use sudo. So we have capsys admin to inspect our program. And here's an interesting thing. The kernel knows we have created the program, but we're not able to get access to it without sysadmin. So what's the workaround in this case? Well, in addition to pinning the link, you need to pin the procs or maps so that you can later query them. Okay, we have everything set up. The program is attached. The objects are pinned. Now we want to read the useful stats that we're collecting from a user space map, from a user space. And actually, we don't want to read them ourselves. We want a metric scraper that is running with different credentials to do it. So first thing we need to do, we need to make the map readable to anyone. Please know that that's not the best security practice, because you can still modify the map from the BPF context. But we're going to go with it. We also need to make the dedicated BPFFS instance accessible to anyone. Once we've done that, we can simulate what the scraper will be doing by running BPF tool map dump as the scraper. And surprise, well, it's not allowed to dump the map. Why is it failing? Well, it can't get an FD for the map. So we have to trace again, and this time we get as far as inode permission. What do we do here in inode permission? Well, we actually compare the access rights to the pinned file against flags that we passed in file flags attribute in the BPF syscall. And unfortunately, the flags, if we don't set them, are translated to read and write requests by default. That is actually what BPF2 map dump is using. It's requesting read and write access by default, even though it probably doesn't need to. Not a problem though. We're just gonna write a custom dumper that shouldn't be too hard, right? Except it is a little hard because libbpf doesn't allow you to set file flags. So you must call the BPF syscall directly, and glibc doesn't wrap the BPF syscall, so you end up with the snippet of low-level code. Right, so after making our panda set 9 times by my count, we can test our program. We'll run ping in the background as a transient service, and we can attach our packet counter to the C group created for that service. And as a scraper, using our custom helper for dumping the map, read out the packet count. Right, and that's all from me. Here are all the issues we've run into on the way, if you would like to discuss them afterwards. The code for everything I've shown here is on GitHub, but I encourage you strongly to try to build it yourself and try to troubleshoot the issues. And I'm happy to discuss any of this after the talk. Now, in the sake of staying in the time slot, I'm going to pass it on to my colleague Arthur to talk a little bit about problems with auto-generating BPF. Thanks.
Thanks, Jakob. Can I get access to the slides, please? I don't think I can move them. Awesome, thank you. So now on to auto-generated BPF and issues we have there. So for a bit of context, we mainly use this as part of our distributed denial of service mitigation pipeline. So the basic idea is we just want to drop all the DOS packets. And so we have a separate mitigation system, and we're not going to cover that today. It's like an offline separate thing that generates classic BPF. And this is classic BPF in the sense of libpcap or TCP dump. And we push all these rules, which you can see right here, down to our servers, and the goal is that they just drop packets. So in this silly example, orange is all the attack packets, and only the blue, nice, safe packets make it through. And so we use classic BPF because it's super flexible. We have tons of sources to generate it. So the most common one, of course, being libpcap or TCP dump, but we also have custom generators that can match, for example, on DNS query host names and DNS packets, and also a bunch of just handwritten classic BPF assembly. And even cooler, we can run it in a bunch of places. So today we run it in IP tables with XTBPF, like Jakob showed earlier, and we also run it in XDP with CBPFC. And this is a little tool to compile classic BPF to C, and then we can compile the C to eBPF with Clang. And this is kind of how it ends up looking. So we have all of our classic BPF rules. And so typically we have hundreds of these rules at the same time. And so at the same time, we end up with hundreds of IP tables rules. But we don't really want to have hundreds of XDP programs around. So we compile all these down to one C file and then build that with Clang and load it as XDP into the kernel. What could go wrong? Well, it turns out a lot goes wrong. We see two main different kinds of failures. The first one is eBPF that we've generated that is rejected by the kernel, by the verifier. And this is even ignoring kind of intrinsic limits like the maximum stack size or the maximum number of instructions. And these general problems are the same that you have when handwriting BPF. There's just no human to go fix the problems in between. So the classic ones are like packet accesses and division by 0, but we mostly figured those out. But this still remains the hardest part for us, especially with all of our classic BPF rules combined into like one C file. Clang loves to do all kinds of dark magic and crazy optimizations that tend to break things. And the failure mode isn't great. When this happens, it kind of freezes our whole DOS mitigation pipeline, so we can't add or remove rules anymore. And the second kind of issue we've seen before is incorrect behavior. And this just means that we generated eBPF that passed the kernel verifier, but it just doesn't do the right thing. So either we drop the wrong packets or we don't drop anything at all. And what sucks here, of course, is that it's hard to notice, and these issues are really hard to debug, because it's kind of just occasional packets randomly go missing. So of course, BPF is good for testing, and we have lots of unit tests to try and fix these problems. So we have unit tests pretty much for every known classic BPF rule we have, and we can test this pretty easily by compiling them. So here with our usual pipeline, so we take this BPF, convert it to C, and then compile that to BPF. And then we can just load it into the kernel. And when I say prog test run here, I'm kind of conflating it with loading the program at the same time. And so we can check to make sure the verifier accepts the program and that loading is happy. And then, of course, we can use prog test run, where you get to feed a specially crafted input packet through a BPF program and get the result to make sure it matches. But the problem is that this can only cover so much. All our rules are parametric, so we can have the same rule, but for different IPs, different ports. And we have hundreds and hundreds of rules, and we can have handwritten BPF. And combining all this, it's just not feasible to write a test for everything. And unfortunately, we still see failures in production. And so the idea was to start testing what unknown filters we haven't seen yet. So of course, we can just generate some random CBPF instructions, and we can load them the same way with BPF prog load. But how do we know if that's valid? How do we know if it should load? And it's the same problem with correctness. Of course, we can load a random program. We can run a random packet through the random program, but how do we know if it should match or not? And thankfully, this is where the flexibility of classic BPF comes into its own. Of course, there's a reference implementation. So classic BPF is also used for socket filters. And so we can attach our original classic BPF input program as a socket filter on a Unix socket and use that to figure out what our random program with our random packet should do. So if we can attach the socket filter, then our compiled program should load. And if the socket filter drops the packet, then so should our program. And this ends up looking like this. So we have here just kind of a random source of classic BPF. And so it generates classic BPF in a packet. And the packet goes through the reference source. And it tells us if this filter is actually valid and if the random packet should match it. And then here we can test our own implementation and see if we also think it's valid or it also matches. And anytime these disagree, of course, that's a problem. But part of the problem is that it's hard to exhaustively explore all the possibilities here. We're just kind of generating random input and seeing what sticks at the wall. It'd be cool if we could kind of exhaustively search the space. And so it turns out we're just one step away from fuzzing. And the idea with fuzzing is that we can have a fuzzer here that starts off with an initial corpus or kind of sample classic BPF programs, loads them and runs them through our normal test pipeline, so CBPFC, and at the same time instruments it to get information about which program counters and which code paths were actually covered by this. And so then when it's making random changes to this corpus, it can figure out which random changes are interesting and did more code coverage and we should keep, and which ones did nothing, where we changed something random, but it turns out that was just like changing load 1 to load 2, and it didn't actually make any changes. So nothing would ever break. And so this is kind of what it's ended up looking like. So it's the same thing as before, except now that we have GoFuzz, and this is a standard-ish Golang tool for fuzzing Golang libraries. And it generates both the classic BPF and the packet, so it's kind of almost like two-dimensional fuzzing. And this is important because it means it's fully deterministic, and that when we have crashes, we kind of have the whole sets of input preserved as one thing. And of course, we get CBPFC is instrumented, and we get coverage back into GoFuzz. And so this was cool, and it works, but it was really slow. And the time to first bug was in days. And that seems typical, I guess, when you look online at other fuzzing examples, but we know there's a lot of low-hanging fruit here. And so a big part of the problem, I think, is that we don't have code coverage for the most interesting bits. So we can cover and instrument our own little compiler, but there's only so many code paths there. It's not that complicated. But what we don't have coverage for is like the BPF VM, the BPF verifier, and the same things on the socket filter. So whatever converts it to eBPF. And so this is where kcall comes in, which actually turns out is a way to just collect kernel code coverage. And we can just read covered PCs from user space for the current thread, and it's really easy to enable and disable, so you can collect information for just the syscalls you want to collect for. And this is what powers syscaller. Now, unfortunately, there's no easy way to hook this extra coverage information back into GoFuzz that I could find, but it's okay because we can use libfuzzer, which is also what syscaller uses, and that's super flexible and lets you specify tons of additional coverage sources. And the cool part here is that we can end up with one fuzzing engine here that still does the same as before, so generates the classic BPF and the packet and runs it through the whole pipeline. But now it gets coverage from converting the classic BPF to C, from loading and running the eBPF program, and from loading and running the socket filter. So it gets covered for pretty much everything except for Clang. And this is a lot better, and it's really cool because we have like a combined fuzzer with user space and kernel space coverage. And in this case, the time to first bug was more on the order of minutes than days. I mean, not single minutes, but like 10 minutes or so. And it's found some cool bugs. So one of those is that we try to insert as few packet bounds checks as we can, because it really adds up to a lot of instructions. And in some subtle cases, we just kind of forgot to add some. And it turns out we also didn't check for overflows. So the verifier enforces that offsets that we add to packet pointers need to be less than 16 bits so they don't overflow, and we didn't check that, and that requires runtime checks. Yeah, so we found lots of these cool bugs, but we also found a bunch of bugs that well, not a bunch, but a few bugs that we really don't really know what to do about. So one of these is Clang optimizing out packet bounds. So we write code that has a packet bounds check, and then Clang just gets rid of it or mangles it. So here's a small challenge. Try to read the last byte of a packet, just in C, with no ASM hacks. And so this is, I think, what it would look like in XDP. So we just load, the normal data endpointers from the XDP metadata, figure out what the size is, and then do a bounds check. But of course, this bounds check is kind of nonsensical because it's computed based off of data and data n, so this is never going to be true. And then finally, just read the last byte. Now, of course, this doesn't work. Clang is both really smart and kind of silly. So it's really smart in that Clang figures out that we're just trying to read the last byte of a packet, even though we never read from data end, and it only loads data n. So Clang doesn't even load the data pointer from the XDP struct, and it literally just reads the last byte. But of course, the packet bounds check becomes quite silly, R1 greater than R1, which is really kind of nonsensical. And yeah, it's not quite clear what exactly we should do about this. Should we have a magic annotation to help Clang not optimize out bounds checks? It seems like that could help, but then again, lots of these bounds checks can usually be optimized and removed, and that does help sometimes with code sizes. A similar thing we found is register mirroring. This is what I'm calling it. I don't think this is an official name. But the idea is that Clang takes two registers that are copies of each other and applies the same operation independently twice. And then Clang knows they're the same value, but the verifier does not. So if we start off here, R3 is just some random packet data that's been loaded. And we copy it into R4, so now these two registers have the same value. We do some bit shifts on this one to make sure it's 32 bits. And then here we do our overflow check. And we do this on the copy that's had the bit shifting done. And so we can see that as soon as we do the bit shifting, of course, the verifier gives it a new ID, starts tracking the max value, our overflow check works, and we get a sensible max value that's less than 2 to the 16. Great so far. But then when we're doing the packet load, Clang uses the original register, R3 from up here, does the same operations to it, so at which point it has the same value as the copy we've made here that we have bounds checked. But of course, the verifier doesn't know that and still thinks it has a humongous Umax value, and packet accesses don't work. And so in this case, somehow Clang is kind of correct. It's like semantically, these registers do have the same value, but how can the verifier figure that out? That seems to me innocently like a really hard problem to fix in the verifier of tracking which registers have the same values based on what operations are done. And maybe there are some magic C casts or things we can do to this, but I couldn't figure anything out to fix this. And so with these bugs, we started thinking about, is a world without Clang better for us when we generate eBPF? And could we generate eBPF directly ourselves? If we do it ourselves, we can make sure that we're never going to optimize out of bounds check or mirror or register or put a packet pointer on the stack. And this is something we've had problems with before, packet pointers on stacks and the verifier not tracking all the attributes. But I wasn't able to reproduce it the other day, so maybe that's just magically fixed. If so, thank you. And we also thought that we might still be able to have our cake and eat it because we can handwrite some of our C code and then link it to the auto-generated BPF and kind of keep it all. And so this is supported today in our CBPFC library. It can also generate directly eBPF, and we test it and fuzz it the same way as we do the C backend that we talked about before. But unfortunately, this didn't turn out to be a kind of universal solution. So here's another example where there's more space, so we have more context. So we load So R2 is just the packet pointer, and we load 1 byte from the packet, fair enough. And we've already done the bounds checks and everything here before, so this is allowed. And of course, we're loading a single byte, so the verifier decides that the UMax value is 255, fair enough. And then we do something a bit nonsensical here. We compare it to 512. So of course, a single byte is always going to be less than 512. But in this case, if the byte is less than 512, we jump somewhere else. And so if we continue down this branch, the byte has to be greater than 512. And to its credit, the verifier tracks this. The minimum value is now 512, and the max value is 255. But of course, this doesn't make much sense. And as soon as we try to add this offset onto a packet to dereference it, it just becomes invalid, and the verifier rejects it. Now, of course, this code is nonsensical. It kind of just doesn't make sense. And also, interestingly, it doesn't happen with Clang. Clang never generates, as far as I can tell, stuff like this, because it's also smarter and tracks the values of variables and knows that a single byte will always be less than 512. So this only happens when we're compiling classic BPF directly to eBPF. But in other ways, this seems kind of like a legal, like an allowed thing. In any other language, if we write normal C code, this would be dead code, but it would be still allowed. And so should we fix the verifier to allow this? Can we somehow, it seems like the verifier has enough information to know this is dead code. Should it just ignore it? Or should we deal with it in user space? And that seems like a harder problem, because it means we'd have to go re-implement all of kind of the variable range tracking to know the UMax and UMin all in our library, on top of what the verifier is already doing. And so yeah, that's it for all the bugs. Fuzzing isn't perfect yet. Right now, we do have lots of problems. One of them is that it's hard to suppress errors. So even with the program counters and the coverage, the fuzzing does tend to generate the same error over and over again. And I think the typical way this is suppressed, and like errors are like future errors that are the same are ignored, is based on like matching the error string or the output of the program. But of course, the verifier output changes with all the instructions, so that's kind of hard to do. And we've also gone to the point where there's just so many errors when fuzzing the C backend with Clang that we've kind of stopped. But yeah, it seems like it would be cool if maybe we could suppress errors based on the program counter somehow. It doesn't seem like this is something libfuzzer supports. Maybe we could go do it ourselves. We're also using kconf with the BPF JIT and the interpreter, and I played with both and we get similar results, but it's not quite clear if one is better than the other or if there really is kind of a meaningful difference. And so just remember, this was done with Clang 13. Well, that's what I put on a slide, but I realized that it's actually Clang 11, so this is wrong, ignore it. And on an LTS kernel, and the test cases are on GitHub. And a PR to implement all the fuzzing I've just talked about isn't yet up, but hopefully it will be in the next few days. There's a few loose ends to wrap up. And that's it. Thank you very much.
All right. Thanks so much for your presentation. Now opening up for questions. If anyone, I see John raised his hand. Please pick up.
Yeah, I had just one of the bugs you were pointing out looked like a bit shifting bug, right? I think you went a little bit faster than I could follow. I think it was on like 74 or 75, but it looked like you weren't using ALU32, and I think a lot of that is the compiler trying to zero the upper 32 bits, which it has to do because it's C, and it doesn't know, it has to zero the upper 32 bits. I think you will fix those if you use ALU32 and a new Clang, like Clang latest.
Okay, thanks. So I'll definitely give that a go.
Yeah. Good.
I was trying to find, I think I've seen this before with additions as well, where Clang takes a register and adds the same constant to like 2 different copies, but I couldn't find it anymore. So maybe I was just dreaming.
Yeah, I would try the latest Clang for some of that stuff.
I think there may have been a follow-up comment from Lawrence.
Yeah, hello. Some time ago, I tried enabling LU32. I'm not sure how well that went. Yeah, I should have sent something to the mailing list. I forgot about it, sorry. There was something where you kind of need to make sure that certain variables stay 64-bit, otherwise you lose certain bounds, at least on the kernel that we use. So So it's a bit hard to keep it straight what's been fixed upstream and what we have, because all of our production is basically always on LTS. But it's a good suggestion, John. Thank you.
So there's a question from Toki. Please go ahead.
Yeah, I think I've run into the register mirroring thing with manually written C code as well at some point. So having some kind of general solution for that would be awesome, because it's really annoying to debug. I had another question. So on the CBPF to eBPF thing, it seems to me that this is a sort of generally useful thing to have, right? The ability to match unpackaged metadata and use all the CBPF generators, the PCAP and so on. And since we already have an execution engine for it in the kernel, would it make sense to be able to just hook into this from eBPF, like a helper that you can load the CBPF bytecode separately, and the kernel will make sure that the semantics match, and you can just like BPF call into something that will give you a match or didn't match?
That's definitely a really interesting idea. I never thought about that. Yeah, I guess that would work too. That'd be kind of cool. Yeah, that sounds really interesting. Something to look into for sure.
Right, there's a question from Andre.
It's more like a comments, mostly about second part, because I already forgot the first part of the talk. Can you go back like a few slides? So on the register mirroring, like Young Hong and Alexei could correct me, I think we tried to fix that issue in latest Clang. So like always try latest Clang. We try to minimize at least like that. But this problem with data and plus size and the compiler optimizing this, right? We've had some success using a very simple macro, which I'll paste in the chat, like I called it barrier wire, like you can find it in self-test. It essentially makes a variable sort of unknown to the compiler. So it should avoid optimizing this size check. So try that. So insert this barrier wire after you calculate size. So between size and between doing the if, that should help. And that should help actually with some other cases. So for example, like in this case, you say that U64 casting didn't help you, right? It's because Clang is so smart that it tries to delay this U64 cast as long as possible. Sometimes just avoids it when it can prove that, you know, like it doesn't matter and all that stuff. So this barrier wire also helps in those cases, because you just say like, compiler, don't assume anything you know about the variable, like treat like it was rewritten essentially. That's what the assembler says, like it's no op, but it says that, you know, variable comes in through the register, comes out, and like, you know, because it's assembler, compiler cannot assume anything. There was something else. Can you go back like a few slides? While I'm
before we go to the other slide, I will just have a quick comment on this one. So yeah, I will second John's suggestion of trying MCPU v3, and which is turns on the 32-bit register mode, and it's actually default in the Clang. I forgot since which version, because in general it produces beta code, which not just beta code, it's shorter code, and it performs better in most of the cases we've tested. I forgot the exact percentage gain. And what we found that on most of the tests, it gives better verification results. So the code with the latest with MCPU v3 and LU32 has a much higher chance to pass through the verifier. Then regarding all of this, what you call register mirroring, there was actually, we identified about 5 different cases within optimizations within Clang that was causing this, well, optimizations that are unfriendly to the verifier. And we didn't quite disable them, because we cannot really disable optimizations in general in Clang. So what we did, we introduced special built-ins and passes inside the verifier where certain parts, let's say, of the optimizations get like becomes somewhat invisible to the backend, and this parts of the optimizations no longer happening. So, and this is all, again, I don't remember which Clang version it all went in, but it's relatively recent. recent meaning like around 9 months, maybe 6 months or so ago. So if you are on Clang 11, yeah, that's definitely would be way too old for all of this to happen, to be observed.
Great, thank you. Yeah, I'll definitely try with a more recent Clang and MCPU v3. That'll be interesting, yeah, because for the direct eBPF, we use ALU32, and that does work really well.
So if I may, like I did actually have the question. You were mentioning like that you are linking the handwritten C BPF code to the auto-generated C code. Like how do you do that, and whether you tried the libBPF static linker for that? Because that seems to be a good case for that.
No, I haven't tried the libBPF static linker. We use everything is Go, so we use the Cilium eBPF library. And as far as I know, there's no support for that yet there. And right now, when I say linking, we're just kind of embedding it almost. So we're like rewriting, like I have a hacked up version that just rewrites the ELF to insert the instructions in the right place. But hopefully at some point we can move to a nicer API.
Okay, I was imagining that you would produce like a separate ELF file just with like your auto-generated code and then actually link it to another ELF file generated by Clang. But yeah, like for Go, it probably won't work. All right.
I had one more thought, maybe like for the register mirroring. I think like if we would implement that in the verifier, I'm not sure, but my assumption would be like it would probably really hurt path pruning potentially quite badly. My assumption, or I mean, maybe it would just be like a naive implementation, but you would probably have to mark all the registers, and whenever they change one way or another, you would have to add like a new ID to them, so that you don't propagate information to those that don't have the same ID, for example. But maybe that's a better option. I don't know, but
I think you and Clang already did that for simple case where the registers are just copied and not modified. But very often Clang, like in my practice, right, Clang would copy the register, will decrement one of them by 1, and then assume that the relation between them is like ±1. And that's what's hard to track. So like I think we, in latest verifiers, we do track when the registers stay exactly the same until they are modified. That's what I think you and Clang like added that to verifier, but I don't know. But like when you actually go and modify ±1, then
Andy, you're talking about this, yeah, the ranges. It's part of the common sub expression stuff. It's not the full optimization pieces of it, but responsible for it. And yes, this was addressed in the latest LVM. So just in general, like comments. So thanks, folks, a lot for the feedback. Like absolutely acknowledge all of the issues you mentioned. They are real, no doubt. And with the environment that you described, this version of the Clang, this version of the kernel, absolutely the users will hit it, and that's usability constraints and certainly makes for the poor user experience. This is understood, and I think everyone is working hard to fix those. This is highest priority in general, like improve the user experience. But please try the latest kernel and the latest Clang, because there is constantly like effort to improve stuff. So this feedback would be more valuable if, like you say, well, we've tried on the latest Clang and latest kernel and we still this issue. Then it would be like very actionable. Like from this, it's hard to make step forward from here, like from this register mirroring. Well, is it a real issue now? We believe we fixed it all from what we've seen. If you still see it, please try with the latest Clang, latest kernel, and if it's still there, we'll be happy to like go back and see whether we missed anything.
Yeah, that makes a lot of sense. I'll definitely give it a go with the latest kernel and like nightly, like BPF next and like latest Clang for sure, and report back if we find anything.
Could you go back to all the sad pandas? Because I feel like we should also talk about those a little bit. It's slide 54. Do you want to? You can probably select it directly from. Meanwhile, there was a comment from Paul that I can just read for the audience. So he mentioned we use ALU 32 attribute for LVM in Cilium to remove those shifts, but only on the latest kernels, because verifier had some issues on older kernels. And with MCPU v3, it also helps for verifier complexity and the number of instructions. Yeah. Cool. So yeah, I think like it seems like a lot of these are potentially also fixable from the kernel side. Did you can we expect some of those as patches from you, or so I'm like, just to give an example of, like, for the file system that you mentioned, where you need the user and group ID as owners. Have you looked into that? Maybe it's trivial to do. What are your thoughts here?
Yeah, definitely. I mean, we'll try to contribute as time allows, but also I wanted to list the issues because sometimes people are looking for, projects to get involved, and they perhaps don't know where they should get started. And like you mentioned, some of these issues seem easily fixable. Some of them are in the user space and libbpf. That would be a great place to start contributing. Yeah, but we want to smoothen out the user experience as well, because that would also translate into our configuration in production. That would be easier to maintain.
Yeah, definitely makes sense. I mean, absolutely. Thanks for bringing all these up. I was wondering, like, given we removed the R limit some time ago that you mentioned, do you have any experience now that it's moved over to the memory C groups? Did you run into anything on that in production, or yeah?
So we're still waiting to take benefit of that, because we run LTS. So all our prod is still on 5.10 at this moment. And yeah, ask me again beginning of next year.
I have a follow-up question, because I don't understand like the real world implications. Like, what if you actually increase this R limit to infinity, like for your user? Like, what bad would happen? And the context for this is that I thought about like doing this by default in like libbpf 1.0 mode for everyone. Like, if the kernel is old, then just like bump the R limit to infinity, because it's like the constant pain and everyone is like just forgetting about this. But I'm wondering like what will be the downsides of doing that? Because I think in practice, a lot of applications that I saw actually do the infinity and forget about this. But I don't know, it seems like you are very cautious about this. So I wonder what's the downsides.
Yeah, so I think when I was testing it, if you just constantly try to allocate the OOM killer will kill you at some point, which is not a huge problem, but that's definitely something that we try to avoid popping up in production and causing alerts. So that's more like a security guard that we want to have for any service, that your allocations don't go out of what you expect them to be. So it's just in case, just a precaution. And also,
like,
I guess
library like if like libbpf will Go library, right? Like, would just bump it to infinity. What would go wrong? Like, would it be that bad? Because like I can find many other ways how the user space application can exhaust like whatever resource in the kernel, right? So this specific R limit seems to be causing more pain than actually benefits.
Right. So I just remember what was our other concern. So to bump the limit, you need capsys resource, right? That allows you to change other resource limit as well. So if possible, we try to run with least possible privileges. So that's a pain point there. But I don't know, and I don't remember if you can affect other workloads by just going wild and allocating as much memory for BPF maps as you possibly can with a limit set to infinity. Yeah, and also it's fair to say that this was fixed, so this is just something to know of until you phase out the LTS kernel, and soon it will no longer be an issue, at least for us.
I think in terms of stuff that we would work on, I think one thing that's kind of tiny, and we've been discussing this, Daniel, is kind of at least make this JIT limit better discoverable, I guess, and being able to read out what's the current value, stuff like that. I still think it's, well, we learned about it last week. We're still kind of trying to work through the implications. Yeah. I think it's kind of worrying, to be honest, because we have many different kind of teams writing stuff. But I have absolutely no idea how to fix it, right? So I think the best we can do is put it up for discussion. Another thing that is, sorry, yeah.
No, go ahead. Like we actually we have to switch now because it's already 40. Okay. We probably need to move this or like continue to discuss on the mailing list. But definitely good that you brought this up. Okay, so thanks again for your presentation. It was very interesting and good discussions. So the next one will be from XTP to Socket, presented by Judip and Martin. I'm not sure like who, which of you will start, Martin or Judip. Okay, so I will make you the presenter. 1 second. All right. Judip, so you're not the presenter. I think we cannot hear you yet. Could you unmute yourself just in case you're... We still cannot hear you yet.
Hi, can you hear me?
Yeah, we can hear you. Perfect.
All right. Okay. Sorry about that. I just had to disconnect and reconnect. Okay. Sorry for that. So hello, everyone. My name is Udip. I work in traffic in Facebook with Martin from the kernel team in the Facebook. I'm going to talk about the routing of the packets from the XTP layer all the way to the application socket in the traffic in Facebook. A little bit about this talk itself. In LPC a few years ago, we shared how we run different services powered by XTP. And to this day, a lot of XTP-based applications like full load balancer and firewalls continue to power traffic in Facebook. For example, every single packet process coming towards Facebook has been, or still now, is processed by the XTP-based a lot of these firewalls as well as load balancers. And in today's talk, I want to basically start from the XTP layer and go into more details into some of the problems we face in actually consistently and efficiently routing the packets all the way to the reverse proxies application layer. Specifically, I'll go into details into the two different BPF programs. One is the BPF type SKU port, and another one is BPF TCP header options. That helps us simplify the problem in picking the socket both within a host as well as picking the right host to route the packet. Here's an overview of the overall talk. So there are two different parts to it, as I mentioned earlier. So on the part one, I'll start with what we call as zero downtime restart of the layer 7 service. I'll start with the motivation and describe what that is, some of the problems with our existing approach, and we'll go into details into how BPF SKU port help us solve those problems and help us realize a lot of efficiency and operational wins. And then on the part two of this talk, we'll go into the details on some of the mechanism used by the layer 4 load balancer to pick the backend host, which is based off of the consistent hashing, some of the problems that we face with today's approach, and how we're able to actually solve that problem by embedding the routing information in the TCP packet itself using BPF TCP header options. Before I begin, I just want to provide a brief overview of the traffic architecture in Facebook. So we have two tiers here. One is the edge tiers, which are around the world, and we have data centers. In both edge as well as in the data centers, which we also call origin, they are both the layer 4 as well as the layer 7 load balancers. And there's long-lived connections, typically long-lived connections from edge to the origin via backbone. As you can expect, pretty much all the user connections terminate at the edge, and both in edge and origin, there is a layer 4 load balancer, which basically load balances the incoming web-bound traffic to the individual layer 7 host. And the layer 7 service basically load balances at the end in the origin to the individual servers, such as HSVM or many other different applications. Okay, now let's go into the part one of the talk, which involves more in how do we route packets within a host, in other words, with the zero downtime restart. And in this part, I'm going to be focused more within the layer 7 aspect, both in the edge and the origin. Before I begin, I just want to point out that we have described the overall process in detail in the SIGCOMM paper in the last year's SIGCOMM. So for those of you who are interested in more details to figure out what the actual implementation level details are, you can go and read that paper as well. So, okay. So if we, whenever we want to restart a service, right, like in this case, let's say layer 7 reverse proxy, a very traditional approach to restart the service involves something like, so at a given time, you have some number of existing connections, and each of the hosts is also accepting new connections, right? And then when you want to, let's say in this case, let's say we pick a proxy zone 1 to restart that, then it involves something like a graceful shutdown period where it stops taking any new traffic, but at the same time, it is serving the existing traffic so that the existing traffic has, existing connections have chance to terminate gracefully, organically, so that we avoid any kind of like spikes in the user visible errors, for example, because of the TCP reset. Usually this is achieved via failing the health check from the downstream service. Like for example, in this case, we would basically have a mechanism where this particular host would fail the health check coming from the Catran. And after a period of time for the graceful shutdown period, which can usually be in like order of minutes, like 5 minutes or 10 minutes, depends on the application, then it stops actually to accept any new traffic as well, after which you'd go and deploy the new code there. So you terminate the existing process and you spin the new process with the updated code. And after a period of time, the number of connections starts to ramp up, and you have the new updated process that is actually taking the same level of connection that was before. So far, so good. It works. It's been used by many organizations and services. So what's the problem with it? One problem is that when you are actually doing the deployment, you are at a reduced capacity. And it really depends on how you have configured it. But at the end of the day, the time period, including from the graceful shutdown period all the way to the time when you have actually spun the new process, that is the time when you are not actually serving the maximum number of connections that you actually could be serving. So you are at a reduced capacity. I mentioned CPU here, but it could be memory or network or any other resource bottleneck that you may actually have. And this is one of the reasons why a lot of the organizations basically avoid deploying at the peak time. For example, you may have to wake up, at Sunday morning at 5 a.m. to actually do the deployment of your service. Now, the flip side of this argument is that, well, you could basically expand the number of phases you need to actually deploy. So there is not any effective hit in the capacity, but it takes forever to deploy, right? For example, if you have 100 hosts, you could basically update one host at a time and do the update in 100 phases, but it's gonna take 100 phases. So, if the graceful time that you have is, let's say, 10 minutes, then it's gonna take 1,000 minutes, which is a long time. And it's basically not gonna scale if you have a lot of services, a lot of hosts, etc. So then that brings us the question like, okay, how can we actually do this kind of update without actually impacting the user traffic, without sending reset to them every time we do the deployment, without losing capacity, and still being able to iterate at a very high velocity. So this is when we introduce what we call the zero downtime restart, or in other words, socket takeover. Again, the details of this mechanism are in the paper, but I'm just gonna go over it briefly. So instead of waiting for the existing process to shut down completely, essentially what we do is we spin another process in parallel, and then we pass the file descriptors of the listening TCP socket as well as the UDP sockets via a local Unix socket and pass the SCM writes. This process works reasonably well for TCP, but there is a problem for UDP-based traffic, especially the ones that actually have maintained connection state, which is the case for QUIC. For those of you who are not familiar, QUIC is an application layer protocol based off of UDP. So kernel doesn't have any context about QUIC itself. Everything is maintained in the application layer. So when we have two different processes running in parallel, then while during that phase, there is no way for the application layer to know where the packet for an existing connection is going to end up in. It could either end up in one process versus the other process, because there is no such thing as like listening socket or accepting socket for TCP. Sorry, for QUIC, like it has for TCP. That's why it's not a big problem for TCP. There are some caveats actually. On Monday, Kuniyuki actually mentioned some of those problems. But even if we ignore those, this is a big problem for UDP-based applications. So to solve this, we essentially implemented a solution in the user space where the new process would basically look up the packet, look up some like metadata. For example, in the case of QUIC, there is what's called a connection ID in the specification itself. And based on that, it would basically forward the, make the determination on which process or which worker owned an incoming packet and make that decision to actually forward to another process via another local socket. So the overall process from like start to finish looks very complicated because there's a lot of the inter-process communication involved. There's just too many states involved in getting this thing over right from start to finish. So if we kind of take a step back and sort of look at this socket takeover process, then it's like very complex and fragile process, as I just mentioned. There's a lot of the inter-process communication involved, which got worse when we had to support UDP-based applications like QUIC. For example, if any one of the process crashes, in addition to the spikes in the user level errors, you would also end up in a state where it is very hard to recover from. There are also known edge cases that would lead in the leaking of the socket file descriptors when it's passed from one process to another. So there are a lot of potential vulnerabilities and paths for outages. So at the end of the day, if we really think about what is the fundamental problem here, then it comes from the fact that we're trying to share the same socket between two different processes without having to create new one. So then we got into thinking like, okay, how can we avoid sharing this kind of mechanism that has forced us to share the same socket between multiple processes? That kind of naturally lends to this discussion with Azure Use Port, where sure, with Azure Use Port, then you don't actually need to share the sockets. You can pretty much spin parallel processes and use Azure Use Port when binding to the socket address. But then the problem with that is, again, for UDP, we end up in a state where when there are multiple processes running, then the packet for an existing connection could end up in any worker or any process. This is even ignoring some of the problems with Azure Use Port that Kuniyuki mentioned on Monday. Now, the flip side of that argument is that, okay, what if you don't use Azure Use Port, right, for UDP? Then, again, we run into problem with UDP again, because for TCP, the single thread that accepts the connection just need to accept the connection and hand over the file descriptor to another thread, which is a very typical setup in a lot of the load balancers. But then for UDP, again, like kernel using on a multiplex, because kernel has no idea whether it's like a new packet or like there is no TCP SYN equivalent for UDP, right? Everything is in application state. So it's going to basically multiplex the packet at packet level. So the one thread which is listening to the UDP socket is going to have to multiply not just the TCP SYN equivalent, but all the packets. So that basically effectively leads into a bottleneck of a single thread, which has to basically process all the packets, which clearly did not scale well for us. So the main key question here is that if we could keep somehow control the routing of the packets within a host, then we could basically not have to do this. We could bind with Azure Use Port in parallel and solve our scaling problem. So that's when we started to think about what if we could use a BPF at the socket level. And this is where we introduced the socket level load balancer, SKLV insert. So with the BPF Azure Use Port, we could basically handle generic any protocol right in the implementation. So the idea is that with each socket family, like let's say port for a socket address, we'd attach the BPF program. And within the implementation of the BPF program, we could handle the routing of the packets for TCP. We could handle the routing of the packets for QUIC, which is a more like application level protocol. We could also handle any like non-QUIC generic UDP because we can basically pick any socket from within that layer. This also allows us better control on the startup process. Like for example, it's very typical that any reverse proxy, when it's starting up, it has a lot of state to initialize. It is also very common for the reverse proxy to go and start like health checking of its pool, etc. Right? So there's quite some time before it's actually, even if it had actually bind to the socket, it's not actually ready to process the incoming packet because there's a lot of initialization happening. So we don't have to worry about that phase because the application level can dictate when it is actually ready to accept traffic on the new process. Meanwhile, the BPF program can send the existing or any new packet to the old process that's still running. It can address our scaling concern. For example, the one that I just mentioned earlier with the single threaded acceptor for all the UDP packets, because we can then bind with Azure Use Port and use multiple workers in parallel. To go a little bit more step forward, this also enables us a generic, like a load balancer type framework. Like for example, it's very typical for any kind of load balancer to employ or enable or offer algorithms such as weighted routing so that you can target more load on certain hosts versus others. So in a similar fashion, we can also target more packets towards some CPU versus others. For example, this can be appealing if you run in a multi-tenant environment where you have multiple containers and they have like uneven distribution of the CPU utilization, where some subset of cores may be harder than the others. So you can basically target the ones that have more CPU headroom than the others. This framework can also offers more ways to actually experiment further. For example, this is still in experiment phase. We don't have any real data on this, but you can basically try to experiment where the packet or SKBF BOF stays in the same CPU or the NUMA domain from ingress to egress, because you can, again, you have control over where you want to send the packet to. Going back to the problem that I mentioned earlier, where there was no way when the two processes were alive for the kernel to for the application to determine where the packet will end up. Now with the BPF, then we can basically put in logic so that even when the new process comes up, all the packets keep going to the old process. And finally, when the new process is ready, then it can update the BPF map to basically tell the BPF program that, hey, I'm ready to actually accept packets for these addresses and so on. The API for the BPF SK select use port offers the SK use port array, which is the array of file descriptors of the sockets for the socket family. And you can pick the index in that array to pick where to route the packet to. So basically the array dictates which process to send the packet to, versus the index can dictate which socket you want to send the packet to. So I mentioned earlier on, you can use this to basically target more load to certain set of CPUs. So if you basically, for example, pin a thread that owns a socket to an individual core, then you can like implement some weighted algorithm just before picking this index to target more load to some index versus others. In terms of the implementation level detail, at the very core of the implementation is like a BPF HASOP map, which maintains the VIP address port as the key, and the value is the, as I mentioned earlier, is the SOD use port sock array, which has the index of the file descriptors. I did not mention, like one of the problems that I mentioned earlier was we still want to be able to keep the packets for existing UDP connections to the old process or the individual worker in the old process. But that can be achieved very easily with LRU hash map, where key is the 5-tuple of source and destination, source IP is destination IP, source port, destination port. And you can just look up if the BPF program has already seen the flow or seen the packet for this flow. In that case, then it can just simply pick up the FD by looking it up and route the packet to that particular socket. As I mentioned earlier, by just updating this particular map, then the new process, sorry, the BPF program can route the packet to the new process. This solved our scaling concern, specifically now that we can dictate how to route the packet from the application level, then we don't really have to worry about the ambiguity to process the route. So as a result, we can basically accept the packets in parallel without having to worry about the disruptions or misrouting or packet drops when the processes were restarting. Just to show you the effect after we made the change, in this graph, I have one graph that shows the percentage of servers in a production tier that were being updated. And there's another graph which shows the number of packets dropped. Basically, when we restarted the entire tier, there was no visible change in the amount of packets dropped while the process was in place. I mentioned about we got rid of our scaling bottleneck. So in this graph, I had two sets of hosts. One is the test and one is the control. And I increased the load targeted to those hosts, starting from load factor of 1, 2x, 3x, etc. On the control host, basically at around like 3 times the load, it was not able to process any more packets without dropping a huge portion of them. So it basically maxed out at 3x the load, versus on the control host, on the test host, which was running the SKLB, I was able to ramp up the load to all the way to 30x. And at that point, basically it was running out of CPU. And even then it was throwing less errors than it was with the control hosts. Just to recap, by just employing a fairly straightforward implementation with the BPF SKU use port and SKU use port sock array, it was able to simplify our overall process and provide us with huge operational wins. There is like no more a lot of the inter-process communication going on to orchestrate the whole process, which means there's overall less failures than now than we used to see before. Got rid of our scaling bottleneck with the single thread, and also got rid of some of the corner cases that led to the drops of the UDP packets. I didn't even mention the three-way, like potential race with the three-way handshake during the TCP connection establishment, which is similar to the problem I described about UDP, because during the TCP scene, the scene ACK could, sorry, the response after the scene ACK could end up in a whole different process. It's the same problem. So we got rid of that edge case as well. So overall, it was a big win for us at apparent no cost other than just the implementation part as well. I do want to share just one experience of deploying this. When we started to deploy this in production, we saw large spikes in CPU when we had these both processes running in parallel, which was very surprising because we hadn't actually seen that issue manifest in our test. And there was no reason to believe that it was gonna, there was like nothing in the implementation itself that led us to believe which would lead in the large CPU consumption. So after debugging further, turns out the issue has nothing to do with the BPF itself, but more to do with the fact that there were multiple sockets within the same network namespace, which were bound both with and without SOD support. There's an implementation of the bind, which basically takes the spin lock to walk along the hash table to find if there is a conflict. But the key of the hash table is just the port. So if you have a large number of HTTP endpoints, then the key is going to be largely 443 or 80 in some cases. And that was problematic because we basically had exactly that. And this was this resulted in like large spikes in CPU and even the host blocking, and took us a long time to actually debug. So we're just saying, just in case someone else have a similar issue, especially if you run multi-tenant environment where a lot of the containers are, for example, run by different teams, and you don't necessarily coordinate with all these socket options that are being applied. So one workaround we came up with was, okay, let's just make sure that in the very early phase of the container, we'll just bind the wildcard 443 so that nothing else could actually successfully bind without SOD support. So this was a way to actually force everybody to bind with SOD support or just crash their application. Even then, we ran into another bug, which has now since been fixed, where, for example, in this particular example, if you bind with the specific address 1 and 2, then the third bind should have failed because it's more generic, but it was not actually failing. So there was basically an implementation bug in terms of how the address were cached in the data structure. So even though it's now been fixed, when we were actually deploying, we had to basically make sure that all the sockets were cleared in that host before we were able to deploy this safely, and then actually bind with the wildcard 443 so that nobody else could actually bind. One more thing, the BPF SK select review support looks quite similar in some ways to BPF SK lookup. So I just wanted to briefly mention some comparisons. And they both seem to have similar motivation. There's actually a lot more detail in this really great paper, which came out in last month's SIGCOMM. So you can definitely follow a lot more in details in that paper itself. And I'm sure Jakob from Cloudflare can provide a lot more details about the BPF SK lookup. But I just wanted to mention that there is some more motivation in that they both kind of stem from this limitation or lack of any control from the application layer to dictate where which socket is picked by the kernel for an incoming packet. There is one, at least one difference in the sense that SK select review support is actually very much tightly coupled with the address of the socket family it's bound to, versus SK lookup on the other hand seems to be aimed towards decoupling the socket from the IP address itself and leads to pick any socket within the network namespace. And now I can go into the part 2, but probably this is a good time to pause for question if there is any. Let me wait for 1 minute.
Yeah, sounds good. Please speak up and unmute yourself if anyone has questions, comments, feedback to the previous slides.
All right, in that case, I can go ahead with the part 2. So in the part 1, we focus on picking of sockets inside a host. Now in the part 2, I'm gonna focus on picking of individual host from L4 to L7. So going back to the overall architecture diagram that I showed earlier, in this part, I'm going to focus within this space between layer 4 load balancer to layer 7 load balancer within the data center. So just a little bit of an overview of the details of the layer 4 load balancer that we employ in Facebook. It is based off of the open source, now open source XCP based. Sorry, I think there's a question. Let me see. All right, I think that's a comment. All right, never mind. Let me go with the part 2, and then I can also answer any questions about part 1 at the end. So yeah, so the outload layer 4 load balancer is based off XTP, and the implementation is open source called Katran. At the very heart of it, it employs the consistent hashing implementation to pick any backend L7 host based off of the maglev hash. On top of the consistent hashing, it also has a mechanism to locally track the connection for resiliency against any changes in the backend server. For example, some servers could be down for maintenance, etc. So to avoid the ring changes, it has a local cache of connections to look up without doing the hash. So here's a very 4-line summary of the overall mechanism to pick an end host for an incoming packet. So for a packet, if it is in the local cache, it just returns that. Otherwise, it employs the hash mod ring. It is very, very efficient and effective. So what's the problem with that? This particular graph is from the maglev paper itself. So this graph shows for 2 different sizes of the ring, the changes in the ring itself when the on the x-axis is the percentage of the failed backends. So even though the summary is that even though the change in or the probability of misrouting on a change in the backend itself is quite low, there is still non-zero chances of misrouting when that happens. And it works very well for short-lived connections, which is typically the case for a lot of HTTP-based application. But it is problematic when you have to support a very long-lived TCP connections. For example, like video streams that go on for multiple hours, or sport broadcasting and so on. So going back to that overview of the implementation that we employ inside Katran, the first part to look up if in the local cache doesn't work if there is an ECMP shuffle, which results in the packets for an existing flow go to a different Katran host than it used to. So which is going to then result in cache miss. And meanwhile, if there is also a ring change at the same time, then there's a small chance that it's going to send the packet to a whole different host. So in some ways, usually continuous release or more frequent release of all the tiers is generally a good idea. But then if we do too much, then it actually hurts the overall reliability of the connection. And in addition to the release, like things like maintenance, especially when you have like lots of servers, things like maintenance happen all the time. So the change in the ring is more of a norm than exception. And in that case, anytime there is an ECMP shuffle, you're going to hurt the active connections. Even though it's a small amount, it does pull down the overall reliability metric. One way to solve this problem is, well, you can share the local cache among all the hosts, but sharing the cache across multiple hosts really sucks, because then you have to address a whole new class of distributed system problem. And especially in this very fast data path, you want to be as much efficient as possible. And doing RPC call in this phase is usually not feasible. I specifically mentioned this was a problem only for Quick, sorry, only for TCP, not for Quick. We in Facebook do use a lot of Quick. It's because in Quick, there is something in the specification itself that allows servers to actually embed routing information in the Quick packet itself. So for those of you who are not familiar, Quick specification has a notion called connection ID, and servers can embed any arbitrary information in the connection ID, and clients must echo that information back. So this basically enables servers to embed some routing information in the ID, which clients will echo back later on. And the Catran in the middle can just look up that fixed offset and extract the routing information just from the packet itself without having to do any kind of hashing or cache lookup, etc. Well, can we do the same for TCP? So that's when we started to think about, well, can we leverage the BPF TCP header option that Martin added to embed similar information in the TCP packet itself? Turns out the answer is yes. So the overall idea is that we leverage the SOCOPS program attached to the C group, and you get callbacks on events such as listen, connect, connection established on the client side, or basically on the each endpoint, active side or passive side. And within this implementation of these callbacks, you can either write this routing information. In this case, we just need an ID of the server, if you are a server, or you can just read the server ID in the packet and extract that routing information and store it for subsequent use later on. So here's what it looks like in the overall execution in the data path. So again, going back to that overall architecture diagram, we have the L7 in the edge, proxies in the edge, Catran in the middle, which is the layer 4 load balancer, and again, proxies is the server side, in this case, on the data centers. We attach the BPF program on both sides. So let's go with a flow. There's a SYN packet coming from the proxies on one side. Then Catran is going to apply consistent hash because it has not seen this connection before. Now the server is going to, in addition to respond by to SYNAC, what it's going to do is it's going to look up its own ID and write that ID in the packet, which in this case is SYNAC. Now let's assume that while this is in progress, the Catran host that had the context about this particular connection went offline, and also some of the L7 hosts also went offline for various reasons. So this is going to lead into both the server ring change as well as the ECMP shuffle, because now all the flows that was owned by the host that just went offline is going to be routed to some other Catran instances. So going back to that flow, now on the client side, it's going to look up the packet that it just received, try to parse the TCP header, and extract the server ID and store the server ID in the SK storage. And then it's going to basically, on all the subsequent packet, it's going to embed that server ID in the TCP packet header itself. Now let's see what happens. So as I mentioned earlier, this now packet for the existing connection is going to be routed to a different Catran host because the one that had the context went offline. But it doesn't have to do anything other than just extract the server ID from the packet itself. Then it's going to reverse look up the server ID and then just route to the host that actually owns this connection. So as a result of this, we avoided any potential misrouting of this packet, which would have led to the TCP reset instantly. Overall, the overhead in the data path is basically just 6 bytes, where the first 2 bytes tell about the kind and length of this packet header, and then we basically resolved 4 bytes for the server ID. We didn't see any measurable difference in the runtime overhead from the parsing of the server ID in the layer 4, but that is an overhead. In terms of implementation level detail, for those of you who are not familiar, the SOCOPS, you can get a lot of the callbacks on a lot of these events, depending on the C groups that you're attached to. In this case, we use these callbacks that I mentioned here. In the case of server side, it's gonna just store the control plane of the load balancer is gonna store the server ID in the beginning in an offline fashion. Then every time there is a connect, then it's gonna embed and subscribe to the write header option on the server side. Likewise, on the client side, every time there's a connection established, it's gonna try to parse the header option. And if there is a server ID, then it's gonna store that server ID in the SK storage so that on the subsequent packet write, it can just embed that information. So overall, the implementation is quite straightforward. Now, I left out the part which involves how do we basically assign the routing information, the server ID, and make sure that both the layer 4 and layer 7 have the same view. There is an offline workflow that just assigns arbitrary ID to each one of the active hosts in the layer 7 and propagates that message to both layer 4 as well as the layer 7 service. Again, this is also another fairly straightforward component, doesn't have any like extra overhead or anything in terms of maintainability. And then the control plane of these both load balancers make sure that they are kept in sync and periodically refreshed in the data plane. And because we employ the similar mechanism for both Quick and TCP, we're able to leverage the same pipeline for both of them. As a result, after we deployed this is a graph from the production from one application that has a very long-lived connections. We're basically able to get rid of pretty much all the background noise, in other words, of the TCP or the connection error coming from the connection resets, which definitely makes a big improvement in terms of the overall reliability of the application itself. It does have a limitation, however. It is only feasible if you control both endpoints. So it is only useful in a typical data center environment where you control both sides. For example, it would be great if we could also make it work from the clients outside of our control, but they are not going to echo back the server ID that the server sent. Also, even if they did, I'm pretty sure a lot of the middle boxes and firewalls would probably drop it anyway. I haven't tried it, but it's practically infeasible if you do not control both endpoints. Just in terms of the recap, we're able to embed the server ID in the TCP header for stateless routing. It doesn't really require any maintaining of any state in the layer 4 host. We didn't really see any tangible cost in terms of like CPU or memory overhead, both in layer 4 as well as the layer 7 side. The alternatives of these are quite complex. You either need to share this state among all the layer 4 hosts, which has a lot of the downside. I think there have been some attempts in the past which try to use some other unused like header options or other fields in the TCP header, like ECR or timestamp. That also has a lot of downside in terms of all the pieces necessary to pull together to actually make sure that you reserve, like for example, last few bytes in the timestamp, and then not all the clients actually echo it back, etc. So a lot of these have downsides and a lot of maintainability costs, which we're able to avoid by just using the TCP header option using the BPF. And that is pretty much all I have. Let me know if you have questions.
Awesome. Thanks a lot for the talk. So anyone questions or feedback, please speak up now.
Hello, it's me again. Thank you for this talk. It was really enjoyable. And I had some deja vu because I think the problems that you've solved are very similar to what we have been solving as well. So it's really interesting to see. I think your TCP header option is really cool. Makes a ton of sense. with being able to control both client and server is also cool. So thank you very much. That was enlightening. I was wondering, we looked at Katran years ago, and there was some, I think we're always a bit confused where I think somehow we got the notion that Katran has a somewhat consistent connection tracking view, I guess, of a colo or something bigger than that. But from what you said, that's not actually true. So maybe you could.
Yeah, so Katran has this, for the connection tracking, it is very local to itself. So that's why if there is a ECMP reshuffle and the packets go to a different Katran, then it's gonna know anything about that connection. So it's gonna basically fall back to the consistent hashing. And in that case, which again, like works most of the time, but if the server ring has changed, then there's a small chance that it's gonna pick a different server. So if you have enough of those connections, then it's gonna show up in your reliability metric, which was the case for us. Yeah, overall, I think the biggest win has been the overall the simplified process as a result of this, especially with the zero downtime reset. There were a lot of very complex pieces, which we were just able to get rid of that and just have like one layer to dictate the overall process regarding the part one.
I was wondering on the consistent hashing note. So you do have this upper guarantee of, let's say, where you can say, okay, at most 1% of backends should change if, for the consistent hashing. Like what? So like what's your experience from practice? What would be like a good upper bound in terms of changing backends?
Yeah, but the problem here is that we cannot. I think one way to answer that question is that like how many can we limit the number of changes of the backends at a given time, and that's hard to control in a kind of like a large system where multiple teams have different responsibilities and they kind of independently update their services. So a lot of these kind of tend to be in batches where you may have some maintenance event which is taking off a large chunk of the production host offline, and in that case you see like huge spikes in the error rates and so on. That's been our experience basically. So on a steady state, it's not a big problem, but when these kind of events happen in batches, then you see more pain on top of those maintenance events. Right, well, I'm happy to answer questions, follow through the questions in the chat as well if you have any questions. Back to you, Daniel.
Yeah, okay, sounds good. So thank you very much for this interesting talk. I really enjoyed it. So let's have a short break of 2 minutes, and then we switch over to the next talk.
Hello.
All right. Hello, Luke.
Hello.
So our next talk is from Luke, Xi, and Amina about the proof carrying approach to building correct and flexible in-kernel verifiers. So please kick it off.
All right. Hi. So I'm Luke. I'm a researcher from University of Washington, and today I'm going to be telling you about work that I've done with my fellow researchers at University of Washington on an alternative approach to building the BPF verifier that's based off of a technique that's called proof carrying code. So to start off, I think everybody here is familiar with the idea that BPF is a really powerful way of enabling applications to extend and customize the Linux kernel. And one thing that's interesting about BPF is that bugs in the Linux kernel are actually very, very critical because the BPF programs run directly in the kernel address space. And so last year at LPC, I gave a talk about applying formal verification techniques to eliminate bugs within the BPF JITs, which are a critical part of the BPF ecosystem. And this year, I'm going to be talking about how to apply some similar techniques from formal methods to see ways of improving the BPF verifier. The BPF verifier is a particularly important part of the BPF ecosystem, and its main job is to prevent unsafe programs from running in the kernel. The way that it does this is that it implements a static analog for BPF programs in the kernel. And right now, the verifier.c is around 10,000 lines of code, and this complexity continues to grow over time. And this increase in complexity leads to two different kinds of issues for BPF developers. The first type of issue is a correctness bug in the BPF verifier. So that's when the verifier accepts some code that it shouldn't. So maybe a malicious application can construct a BPF program that accesses an illegal pointer and trick the verifier into accepting it to cause some damage. The second type of issue is a flexibility or usability issue. And that's something that we've heard about from earlier talks today, where you have a safe program, but the verifier rejects it because it can't recognize it as safe. So right here, I have this little diagram, which is a way of visualizing these two different types of issues. And note that these two sets are definitely not to scale. So on the left here is the set of accepted BPF programs, and on the right is the set of safe BPF programs. So correctness bug would show up as a program which is accepted by the BPF verifier, but is not safe. A flexibility issue would be a program that is safe, but not accepted by the BPF verifier. So next I'll go into a little bit more details on these two different types of issues. So verifier bugs, or correctness bugs that are in the verifier, are very difficult to find and to fix. So for example, just this year, there've been 10 CVEs in the Linux kernel verifier. And these bugs are really tricky to solve because it's been the case where you can fix the bug and then the bug fix actually introduces new bugs itself. And this isn't just due to some silly mistake in the verifier, it's actually because writing a verifier is a really difficult problem. And that's because writing any sort of correct static analysis is really hard. And because when you're writing the verifier, you have to be reasoning about the C code of the verifier that you're writing, which itself is reasoning about BPF programs. So you have to think about code on these multiple different levels. And this is a really hard problem to solve. On the flip side, the BPF verifier is also overly strict. So it rejects some safe BPF programs. And this happens because there are BPF programs that are safe, but too complex for the verifier to reason about. And a common source of this type of issue can be from optimizations, clever optimizations that are introduced by LLVM when compiling C programs to BPF that can elude the verifier's ability to reason about them. And this is also a fundamentally hard problem because it's really difficult to write a verifier that can accept all the different types of safe BPF programs that there are out there. And this problem gets exacerbated as the complexity of BPF programs continues to increase as BPF gets more and more popular. And this can be a really frustrating experience for application developers when they're writing BPF programs. So I have this quote from Jakob that I like that personifies the BPF verifier as a merciless judge of eBPF code. And what he's getting at here is that it can be a frustrating experience when you write a program that you, the author of the BPF code, know is safe, but then the verifier rejects it. So what this talk is going to be about is first, how are we dealing with these issues now? So one way that we deal with these issues is by doing verifier fuzzing and testing. So for example, the Linux kernel self-test has a large test suite of examples of programs that should be accepted by the BPF verifier and also examples of programs that should be rejected by the BPF verifier. And that's effective at finding a BPF program that is rejected by the verifier. They can disable optimizations in LLVM or tweak or slightly modify their C code until the verifier is happy with it. And Another thing we can do is extend the verifier to have more sophisticated static analysis so that it can accept a wider range of safe programs. But these solutions have some limitations. So first, the fuzzing and testing, they can be effective at finding bugs, but the search space for all possible BPF programs is too large to exhaust. There'll always be corner cases in the verifier that'll be difficult to write tests for or catch with fuzzing. The limitation if you're disabling optimizations in LLVM or tweaking the C code is that those fixes might work now, but they'll be brittle as your BPF program changes, as LLVM evolves to have new and smarter optimizations, and as the kernel changes. And lastly, if we're extending the verifier to have more sophisticated analyses, that can introduce the opportunities for new bugs that can potentially let unsafe BPF programs slip through. So the main idea of this talk is I'm going to be discussing our experience with exploring an alternative approach to designing the BPF verifier. And the basic idea is that we want to minimize the job that the kernel has to do by using a technique called proof carrying code. And the idea of proof carrying code is that user space applications who want to download BPF programs into the kernel will produce proofs that their BPF programs are safe. And then the kernel, instead of having to maintain a complicated BPF static analyzer, will instead perform the simpler task of just checking a proof that's been submitted by an application against some specification of what it means for a BPF program to be safe. And this solves sort of both of the types of issues that we've seen in the BPF verifier. The first one is it's correct because applications cannot fabricate an invalid proof that their program is safe. And it also affords applications flexibility because they can choose the best method of generating a proof for the programs that they want to download. So based off of this approach, I'm reporting on our preliminary results on building a system called ExoBPF, which is a proof carrying code system for BPF. And note that this work is a experimental work in progress, so we still have a lot of design and implementation challenges to overcome before this would be able to be actually deployed. But it's just a demonstration of the ideas, of how the ideas work. So it uses a tool called the Lean Theorem Prover to write the specification, to express the proofs, and as a proof checker. And we've developed two proof generators in user space for generating proofs of safety for BPF programs. One of them is based off of abstract interpretation, and it mimics the structure and techniques that are used by the current BPF verifier that's in the kernel. And the second is a heavier weight approach that's based off of symbolic execution and using a SAT solver. And I'll talk more about these two proof generators later. And just to be upfront about some limitations, we don't want to handle some things that the current verifier is doing, such as doing rewrites or optimizations over the BPF programs, and not handling things like specter mitigations. Okay, so the outline of the rest of the talk. First, I'm going to give some examples of bugs and issues that have been found in the verifier, in the kernel verifier in the past. Then I'll give an overview of the ExoBPF system, give a demo of what it's like to use ExoBPF, and then talk about some limitations and discussion of the system. So the first example that I'll talk about is a correctness bug that was a CVE that was discovered and fixed in 2018. And the bug is related to how the verifier handles the BPF instruction for doing a 32-bit write shift. So the semantics for a 32-bit write shift in BPF are that it takes the destination register, truncates that value from 64 to 32 bits, and then performs a write shift. So in this case, a write shift by a constant 31. Now the verifier, when it's doing the static analysis, the way it works is that it tracks bounds for the register in form of an upper and lower bound of the possible values that register can have. And the bug stems from a mismatch between the BPF semantics and how the verifier computes these bounds. So the verifier computed the bounds first by doing the shift, and then only truncating the result after doing the shift. And this mismatch between the semantics means that it can compute incorrect bounds in certain situations. And those incorrect bounds can be used to trick the verifier into accepting a program that uses an illegal pointer. So let's look at a concrete proof of concept that demonstrates this bug. So here on the left, I'm showing a BPF program that demonstrates the bug that used to exist in the verifier. So initially, we're going to assume that we have some setup code that makes it so that R0 points to an 8-byte array. On the right here is a table that's going to show two things. It's going to show the value of that the register R2 will have at runtime, and then also the upper and lower bounds that the verifier will infer for R2 when it's doing static analysis. So at the first instruction, the runtime value of R2 will just be 2 because it's set to an immediate. And the verifier will infer the correct tight bounds of the lower bound is 2 and the upper bound is 2. The second instruction does a 64-bit left shift of R2 by 31 bits. And again, the verifier produces the correct bounds for this result because it correctly implements the semantics for 64-bit left shift. So on this next slide, though, we can see the results of the bug introduced by the verifier having incorrect semantics for the right shift. So at runtime, what will happen is the value of R2 will be truncated to the lower 32 bits, which is 0, and then right shifted by 31, which is still 0. So the runtime value will be 0. But because this older version of the verifier didn't truncate the results until after the shift, the bounds it computes are incorrect. It thinks that the value of R2 at this point is still 2. So this might not seem like that big of a deal. It's just the verifier has some incorrect bounds for some register. But the reason why this is important is because we can actually use the fact that the verifier believes something incorrect about this register in order to construct an unsafe program that accesses some memory that the BPF program should not be allowed to access. So to do that, we can subtract 2 from R2. So then the runtime value will be -2, and the verifier will think that the value is 0. And then just use R2 as an index into our 8-byte array. Now at runtime, if you actually run this program under the interpreter or JIT, it'll access the negative second element of the array R0, which is clearly out of bounds for the array. And you can imagine further complicating this program to access any memory that you would like. The verifier accepts this program because, according to the verifier, R2's value is 0 at this program point. And so it actually accepts this program even though it's not safe. And just to be clear, this bug has since been fixed. Any questions about this example bug? Okay, I will move on. So the next example that I'll give is an example of a flexibility issue that's in the that used to exist in the BPF verifier. It's actually very similar to the one that we saw in Jakob's talk. And the idea is that while the verifier used to track upper and lower bounds for each register, independently, it didn't track the relationship among different registers. So the BPF verifier used to reject this program even though it was safe. So let's look at what this program does. So initially, again, assume that R0 points to an 8-byte array, and also this time assume that R2 is some arbitrary scalar. So initially, the verifier doesn't know anything about R1 and R2. So it believes that R1 can be anything from 0 to the maximum 64-bit integer, and it believes the same thing about the value of R2. And the first instruction copies the value from R2 to R1. Now, that doesn't give us any more information about the bounds of R1 and R2, so the verifier still thinks that R1 can be any value and R2 can be any value. Next instruction checks if R1 is an out of bounds index for the array that's pointed to by R0. And if it is, it goes directly to the exit instruction. So the verifier learns after this jump instruction that R1 has to be in the bounds between 0 and 7, because if it was any larger than 7, it would have taken the other branch of the jump. But it doesn't learn anything about R2 because R2 is not involved in this jump. So it still thinks that R2 could be any value. And then this program accesses the array using R2 as the index. And of course, the verifier will reject this program because it thinks that R2 could be some arbitrary value, even though we as humans reading this code know that that can't actually happen because R1 and R2 were set to be equal beforehand. Now, this problem has been since fixed in the verifier. And the way that this problem was fixed is by tracking equality among the different registers. So here, at the point that we set R1 equal to R2, the verifier will know that these are the same value. And so when we learn something about R1, we'll learn something about R2. But you can imagine slightly more complex BPF programs that will still trigger the issue. For example, if more operations are performed on R1 and R2, such as the shifts we saw in the earlier talk. Any questions about this example? Okay, I'll move on. So the summary of these examples are that we've seen different types of correctness bugs in so where it accepts an unsafe program, and different types of flexibility issues in the verifier will reject some safe programs. So I think the high-level question is, how do we build a verifier that avoids these types of issues? And the idea, again, is to minimize the job of the kernel to only do proof checking instead of implementing a static analysis, and instead do an untrusted analysis and proof generation in user space. So what does this actually look like in the system that we've built? So this is an overview of the high-level structure of XOBPF. So you have some number of applications, each of which has a BPF program that they would like to run in the kernel. And each application can, for itself, select an appropriate proof generator for their BPF program that will look at the BPF program and construct an appropriate proof that that program is safe. And the application will take this proof generator with the BPF program, and then it'll send the proof to a proof checker that's in the kernel. And the proof checker will examine if it's a valid proof that the program is safe. And if the proof is invalid, it'll reject the program. And if the proof is valid, then it can go on and run via the JIT or the interpreter. So great, now we have a complete system, but the question still remains is how do we actually instantiate this into a real system that's practical? So the first thing that we need is a logic to actually write these specifications and proofs in. So a specification is going to be the property that the BPF programs should meet in order for them to be allowed to run in the Linux kernel. And the proof is a formal argument that a specific BPF program meets that specification. So that's very abstract. So let's look at a concrete example of what a logic looks like. So suppose we wanted to prove some simple statement like Socrates is mortal. Well, first we'd have to choose a logic that we want to use to state and prove this fact. So a simple logic that we might choose in this case is first order logic. So what exactly is a logic? A logic is just a set of deduction rules that tell you how you can derive true statements from other true statements. So for example, this right-hand arrow L rule says that if A implies B and A, then B is a valid deduction rule, which makes some intuitive sense. Now the job of a proof generator is to, given some statement like Socrates is mortal, and wants to search for an application of these deduction rules that demonstrates that that statement is true. So an example in English would be all men are mortal, Socrates is a man, therefore Socrates is mortal. And we can make this notion a little bit more formal by drawing a representation of the proof and the rules that we applied to get that proof as this graph. And you don't have to understand the details of exactly what this graph is doing, but the key things to note are that on the bottom is the specification that we're trying to prove. And on the right here noted is just a sequence of rules that we've applied to get to that final conclusion. So a proof generator can be very complex because it has to search through many of these different types of rules and apply all sorts of different logical transformations and that sort of thing in order to derive a true statement. On the other hand, a proof checker can be very simple because it just has to validate that some proof that it's given correctly follows these deduction rules. So to check this proof, you would just look at each of these rules stated and make sure that that rule is being correctly applied. So this is a very simple example of a logic. When we're actually choosing a logic for XOBPF, we have a couple of requirements that we want it to that we need it to meet. So the first is when we're selecting the logic that we want to use for proof carrying code for BPF, we want to pick one that's well understood and one that has a well-known proof checking algorithm. The reason for that is because logics are really difficult to design and implement, and any bugs or inconsistencies that you have in your logic could make it so that the whole system accepts any BPF program. So to ameliorate those risks, we want to pick a logic that has been well studied and that we believe is consistent. The second thing that we want our logic to satisfy is we want it to enable us to write all sorts of expressive specifications. So anywhere from memory safety to things like that it's free of different types of spectre attacks, or maybe you want to specify that your BPF program doesn't leak the value of different registers. Whatever property it is that you want your program to meet, it should be possible to express that specification in the logic. And third is we want to enable, we want the logic to enable various different types of proof strategies for applications to use to show that their BPF programs are safe. And so applications should be able to select the best approach for their specific BPF programs. So maybe if their BPF program is simple, they can choose a simpler approach. Maybe if it's really complicated, they can use a really heavyweight proof search algorithm. So some examples are being able to write proofs for like implementing something similar to what the current kernel verifier does, to doing something heavier weight, like doing SAT solving. So the logic that we've settled upon for using for our prototype implementation is the logic of this tool called the Lean Theorem Prover. And the Lean Theorem Prover implements a very rich logic, and it's rich enough that its most popular application of Lean right now is that it's being used to formalize a large subset of modern mathematics in a project called MathLib. And because it's expressive enough to state and prove these complex mathematical theorems, it's also rich enough to state BPF's program safety and also prove BPF program safety. Another advantage of Lean is that it has a logic that's been thoroughly analyzed and researched, so we have some confidence that it's actually sound. It has an active community of developers of Lean who are working on both the Lean Theorem Prover and itself and working on its libraries. And it has a number of independent implementations of proof checkers for Lean proofs. So there's one in C++, one in Scala, one in Rust, and one in Haskell. And it's good to have these independent proof checkers because that reduces the risk of there being bugs in the proof checker. So there's many different types of things that you might want to specify about your BPF programs, but just in this prototype, in this example, the one that we're looking at is a simple BPF safety specification. So safety means that, for example, it doesn't have any division by zero. The BPF program doesn't have any division by zero, doesn't have out of bounds memory accesses, that sort of thing. So in order to actually turn this into a formal spec, we're going to formalize the execution of BPF programs as a state machine. Each BPF instruction will step from one state to the next state. And our safety definition will state that the program execution cannot get stuck. So no matter what inputs you start with, there's no possible way of getting in a situation where the BPF program can no longer make progress. So to make this more concrete, I'll show you exactly what the safety specification looks like in Lean. If I can share my screen. Let me see. Go. Share a window. One sec. Is there a way that I can have permission granted to me to share screen? Get code 1136.
Could you try again? I just...
Okay, yeah. Permission to capture the screen needs to be granted. Interesting. Is that a problem on my end then? I'm pretty sure that I should have. Let's check. Okay, it might be my issue. Let me try reconnecting. Okay, I'm back. It should work now, I think. There was a permissions issue on my end. Can I be made the presenter again and then?
1 second.
Thank you. Okay, here we go. So what I'm going to show is a little bit of Lean code which defines the BPF syntax and semantics, as well as what the safety specification is. So this file just contains a bunch of stuff required in order to specify what the syntax of BPF programs is. So here, this defines the set of BPF registers. You can think of this as just like an enum in C that says what the names of all of the registers are. So there's some more stuff related to writing proofs about registers, things like that. We have another one that defines the set of arithmetic operations. And then here we define the semantics of arithmetic operations. So there's two functions which define the semantics. So the first says whether or not a particular ALU operation is allowed in a given state. So in our system, we disallow division by 0 and consider that to be an unsafe operation. So in this case, if you're trying to divide some value x by a value y, that's only safe if the value y is not equal to 0. So that just says when it's okay to perform an ALU operation. And then down here, we have another function which specifies exactly what the semantics of each ALU operation are. So for example, add of x and y, x plus y, and the rest of them are exactly what you would expect for defining the semantics of BPF ALU. So using these core operations for saying what the arithmetic operations do, we also define the syntax of BPF instructions and BPF programs. So this defines what the set of possible BPF instructions. So for this prototype, we support 64-bit ALU and jump instructions. So for example, this represents a constructor for a 64-bit ALU register operation, and these values on the right are the fields of the instruction. So this takes an ALU op to perform, a destination and source register, and then the next instruction to run after this one. So that defines the base syntax of BPF programs in our specification. And then later on, we can use this syntax of BPF to define the semantics of BPF as a state machine. And there's a rule, and so what this step says is it's a relation that relates some BPF state to the very next BPF state you get after executing one instruction. And there's one rule for each possible type of BPF instruction. So let's look at just the rule for 64-bit ALU. What this says is if you look up the current program counter in the control flow graph, which represents the BPF program, then you obtain and you get 64-bit ALU 64 instruction. And if this ALU check function that we saw earlier evaluates to true on the value of the destination and source registers. So for example, if it's a division instruction, it has to be the case that the source register is non-zero. And then you run the actual ALU operation to get some result. So for example, if op is division, then you will divide the value of destination register by the source to get some value v. Then you can take a step from this state to the state where you've updated the destination register to be the new value after performing the ALU operation. So it's a bit weird way of writing. It's kind of like writing a BPF interpreter a little bit. And there's just a rule for each possible BPF instruction. Think of it like a big switch case in C. And this defines what it means to execute the meaning of a BPF program. So then given this meaning of the BPF program, we can actually write our specification for what it means for a BPF program to be safe. So skipping some other stuff that's just related to proofs. So first, we define what it means for a BPF program to be safe in a particular state. So if you have a control flow graph of BPF programs, call it CFG, and you have some state of the BPF, so the state includes things like the registers and the program counter, then that state is safe if one of two things is true. If either that state S, there exists some state that it can step to afterwards, so that is, it can take another step, it can execute another, or if it's already terminated, that is, it's evaluated some exit BPF instruction and it's terminated with some result R. So what this means is that this single BPF state can take a step forward. Of course, in order to actually state the full BPF safety, we want to state that all the possible states that you can reach are safe states. So we generalize this in this definition, safe from state, which says that for all possible states S prime that are reachable from S prime itself is a safe state. So that says if you start from some state, there's no possible way that you could reach a state that wouldn't be safe. And then we can finally define our top level for some program is positive into the program, then all the states from that initial state themselves have to be safe. This is sort of a strange way, if you're not used to it, of encoding this idea of a BPF program being safe over a state machine. But the basic idea is just that it never gets into a situation where it can't progress because it's trying to divide by 0 or something like that. So now that we've looked at this back, I'll go back to the slides. So we've looked at the specification, which is one half of the job that XOBPF has to do, and the other half is to implement a proof checker that checks that specific programs meet the specification. And we can do this because there's a well-known algorithm for checking lean proofs, and as I mentioned earlier, there are multiple independent implementations of this algorithm. And one question that you might have is whether or not this proof checker is actually simpler than the existing kernel BPF verifier. Because what I'm proposing is it seems like the proof checker might also be a complex thing that we have to maintain. And the answer is that it is simpler in many ways for a couple reasons. So first, it uses, unlike the BPF verifier, the proof checker uses a stable, well-documented algorithm that is unlikely, if ever, to have to change over time because the lean proof format is pretty much set. And then secondly, the proof checker is independent of any specific BPF program or any specific verifier strategies that you want to use to show your BPF program is safe. So if you want to add more complex static analysis techniques to accept more BPF programs, you don't have to modify the core lean proof checker. You simply have to write a new way of generating those proofs. And just to give some frame of reference for how complex it is, one of the checkers that's written in Scala is less than 2,000 lines of code. So this is a little snippet of what the actual proofs look like when Lean is exporting them. So this is Lean has a way of exporting proofs to this plain text format that can be checked by external checkers. And you can think of it as like an assembly code for writing proofs and theorems. What it's actually doing is it's a text representation of the graph which describes which proof rules are applied at which step. And the proof checker will take this text file as input and report whether or not all of the proof rules have been applied correctly or incorrectly. So great, now we have a way of submitting BPF programs to the Linux kernel. Now we can just manually write one of these long proof files every time we want to download a BPF program, and then we're done. Except that's going to be very tedious because these programs are thousands and thousands of lines long. It's very difficult to write these manual proofs. So instead, we want to take a different approach, which is to automate the proof generation instead. And the way that we automate the proof generation in our system is we start off by writing a BPF verifier implemented in Lean. So for example, one could re-implement the Linux verifier in the Lean programming language. Then we manually prove once that the verifier is correct for all possible BPF programs. So by correct, I mean that if the verifier accepts the program, then the program is safe according to the abstract definition of safety that we just looked at. And then to construct a safety proof for a specific BPF program, we just combine this manual proof that the verifier is correct with a proof that the verifier accepts that specific BPF program. And so this is a way of automating the proof generation by writing BPF verifiers in user space. So we've done this, applied this approach to build two different ways of generating proofs. The first is an abstract interpreter, and it's inspired by the current kernel BPF verifier and also the abstract interpreter from the CompCert verified C compiler. And it's behaves similarly to the current kernel BPF verifier in that it's computing upper and lower bounds and using tri-state numbers to approximate the values that BPF registers can take on. And the advantage is that it's guaranteed to be free of correctness bugs because any mistakes that we make in the abstract interpreter will be caught by the proof checker. So, but just like the Linux kernel BPF verifier, this one can also reject some safe BPF programs. So to explore sort of a more general approach to verifying BPF programs, we've also explored developing a symbolic execution and SAT solving based pipeline for checking whether BPF programs are safe. And the basic idea of that one is that it'll explore all possible paths through the BPF program and reduce the semantics of BPF down to a single Boolean formula, and then use a SAT solver to prove that that formula is valid. And the way that it works is we use an external SAT solver to prove the formula is valid, and then embed a certificate from that SAT solver into our proof that the BPF program is safe. And the idea here more general than the abstract interpreter-based proof generator, but of course the downside is that it produces larger and slower to check proofs. And the way that it works is that it's effectively in symbolic execution in SMT solving pipeline implemented in Lean. So it starts with a BPF program. It'll evaluate into an SMT expression. So that's like an arithmetic expression over bit vectors. So like 64-bit integers or 32-bit integers. It'll convert that into another representation of Boolean functions called an AND inverter graph. And then finally compile that down to a CNF formula that a SAT solver can reason about. So next, I'll give a demo of what it actually looks like to generate these proofs and check them. So I'll share my screen again. Okay, so let's look at an example demo program that we might want to check using to generate a proof for using ExoBPF. So here's what the program does. It starts by setting R1 equal to R2. It performs some arithmetic on R1. So in this case, it just XORs it with the immediate 1. It checks if R1 is equal to the value 1, and if so, it goes directly to the exit. It just skips the division instruction. And otherwise, it's going to divide R3 by R2. Now, normally, if you just have an in ExoBPF, if you just have an unchecked division like this, it would be unsafe because if it thinks that R2 can be 0. But in this case, this instruction is actually safe because we've checked that that R1 is not equal to 1, and we've also know that R1 has to be equal to R2 XOR 1. And these two facts together will give us a proof that R2 is not equal to 0, and therefore this program is safe. So we can try running this through our script, which will generate a proof using our symbolic execution and SAT solving pipeline. So I tell it to use that verifier, give it a path to the BPF binary of this program, and then tell it to export the proof to this text file. And it takes a little while to do because internally what it's doing is compiling the entire symbolic execution and SAT pipeline down to this low-level proof format. Okay, so it's done generating the proof. Let's look at what it looks like. So it looks very similar to that snippet that I showed in the slides of just lines which encode a graph representation of the proof rules to apply to show this BPF program is safe. And we can actually feed it. We can look at the size of it. The proof itself is actually quite large. It's 28 megabytes. But I'll talk a little bit after I get back to the slides about some possible ways of making it smaller in the future. So we can use a checker. So the checker that we'll demonstrate this on is called Nanoda, which is a checker for Lean proofs that's written in Rust. And we'll run it on the proof. And it takes around, I think, 8 seconds to check the proof. Let's see. 9 seconds. Okay, great. So it tells us that it's checked the declarations and it's made sure that the proof rules are all correct. And therefore, that's a proof that this program that we just wrote up here is actually safe. It doesn't have anything. It cannot divide by 0 no matter what the initial values of R1 and R2 are. Okay, so I'll go back to the slides. It's a little bit alarming to see that the proof size is for even this simple program is so large and that it takes a while to check the proof. But we can break down this proof size and the proof checking process into 2 different parts. So part of the proof is the general proof of that the entire symbolic execution in SAT solving pipeline is sound. And part of the proof is the part that's specific to that specific BPF program. And one way that that we haven't done yet, but that we're considering doing in the future to improve the proof size and proof checking time is to actually cache the results of the general part of the proof so that when an application downloads a new BPF program, it only has to check the part that's specific to that. So this table shows the breakdown of proof size for both the general part of the proof and the part that's specific to that program we looked at. So 28 megabytes of the proof is for the general part that can be shared among different BPF programs. And just 8 kilobytes is specific to that BPF program we looked at. And the proof checking time of the proof checking time, roughly 7.5 seconds is dedicated to checking that general correctness proof, and just 1.3 seconds is spent on checking that specific BPF program. So there's a couple barriers that we would have to overcome before we're able to integrate this work into the Linux kernel. So one is that we need to do more study on the performance of the system on real world programs. So Right now in our prototype, we've tested on programs up to roughly 40 or so instructions, and we need to do some more research and work on making it scale to actual real world programs. We also need to think about ways of possibly embedding the proof checker into the Linux kernel. So for example, if it would be better to say re-implement a new checker for Lean proofs implemented in C, or perhaps reuse existing ones like the one that's written in Rust. And then also there's a lot of effort for implementing and maintaining these proof generators because they require these manual proofs of correctness, which require proof writing and a lot of manual effort in order to write. So those are some of the problems that we're aiming to overcome at some point. So that's the conclusion of what I have to talk about. So ExoBPF is an early prototype for exploring a different way of building BPF verifiers that solves some of the issues that we've seen in the current kernel BPF verifier. I'd like to get some feedback on whether or not this is a possible thing that could lead to improvements to Linux in the future. And we have the code for our prototype at this GitHub link.
Awesome. Thanks a lot for your talk. So are there any questions, comments, feedback from others? Please speak up now. Let me just try to look at the chat because I got dropped in between when you started to share your screen. Somehow it kicked me off. So I would have a question, and then we can go over to the ones in the chat.
Okay.
So how would you? So when you would basically have a BPF program and a proof to it, and then you would submit the proof to the proof checker, and if that goes well, you would basically say that the BPF program would be allowed to execute, right? How do you? So like, I was wondering, how would you? Like from a user space kernel perspective, how would you make sure that the proof actually is the one that really belonged to the BPF program?
Yeah, that's a good question. So I think that's the same as one of the questions in the chat about how does the proof checker know that the submitted proof actually corresponds to the bytecode being loaded. So the way that can be solved is the fact that the BPF program is actually encoded in as part of the proof. And so instead of submitting, say, a separate BPF bytecode and a proof, the BPF program that you want to download could actually be extracted from the proof after the proof checking has been done. So that guarantees that that program that you extract from the proof has to be the one that the proof actually does apply to. So it's a bit hard to demonstrate just by checking the proof and it says, oh, we checked the declarations and they're correct. But you could actually write an extractor that would extract that program from the proof.
Okay, one question. Yeah. So one question from Dave Thaler. Thanks for the talk, very interesting. I'd be interested in investigating possible use of Prevail as a proof generator. The Prevail maintainers have discussed this concept of proofs already and is a direction worth investigating.
Yeah, it definitely is. So Prevail is actually one of the abstract interpreters that we were inspired by when we were working doing this work. So Prevail uses some advanced numerical domains for its abstract interpreter for approximating BPF register values, and we were looking at those and integrating them potentially integrating in the future into our abstract interpreter in Lean. If cached, would the general part of the proof be updated only when?
Yeah. Let me shortly read it for the audience. So if the general part would be cached, would it have to be updated only when we update to a new kernel that would support new BPF features, such as new instructions and so on?
Right. So when new BPF features would be added to the kernel, you would need to update the specification of the BPF safety in the in the kernel. So the kernel is maintaining the specification that says, what does it mean for a BPF program to be safe? And that includes things like the semantics for all of the instructions. You would have to update the kernel's safety specification if new BPF features are added.
I wonder, could that even be like directly built into the kernel? So that you would compile it along with it?
Yes, that's how. So we haven't done anything like that yet, but that's how I envision this working, is that the safety specification is part of the kernel build process that maintains that specification in as part of the kernel, and the proof checker just checks that against the proofs that's submitted by user space.
Question from John. Do you think it's possible to get to good load times with, let's say, 100,000 lines of code, and also will constructs like loops, function, and so on make this better or worse?
So that's something that we're really not sure about yet. So part of the thing that we're exploring is whether or not it's possible to get better performance by using simpler proof generation methods. So for example, if your program this is a sort of contrived example, but if you had a program that was didn't perform any like complex arithmetic, then a very simple proof strategy might work. And it's unclear, maybe it would lead to better proof checking performance and better load times. For things like if you had a very complicated 100,000 line BPF program that also is doing things like complicated arithmetics and loops and functions, it'd probably be both very hard to write the proof generator for that thing, and also the proof would take a long time to check. So we're investigating ways of seeing if it's actually possible to overcome that in the future, but we don't know. We don't have an answer to that yet.
So I also wonder, like in the beginning, you mentioned that you excluded, for example, like the spectrum mitigations, right? I think like they give a whole nother dimension to the complexity, or like the difficulty maybe of proving something.
Yeah, so one way to do it is implement the rewriters that add the spectrum mitigations in user space. And if they're only use like a very specific structure for the spectrum mitigations, then I think the harder part would be writing the specification or to say what it actually means for the program to be safe against those spectrum mitigations. Obviously, you won't be able to, like, if you have some very strange way of mitigating the attack, then maybe the proof generator won't be able to recognize that, but it should, there might be some way of making it more regular that makes it easier to generate the proofs. But I think the hard part is the spec there.
Yeah, I agree. And it's also, I mean, you probably like vendors are also secretive about it, so it it might be difficult. There's a comment from John. I think this execution time will be the main barrier when we did pre-post conditions for loops. It just took too long to load things.
Yeah, that's definitely a concern about the time that it takes to the loading time. The trade-off is that you may be able to, by using some general proof method, you could get BPF programs that accepted that would otherwise not even be able to be accepted by the verifier at all. So maybe in some applications it's worth the trade-off for taking a long load time just to be able to get the program to run in at all. But we'd have to do more investigation on that.
Awesome. Are there any other questions from the audience? Please speak up now. You have 1 minute. Yeah, otherwise this is very exciting work. And yeah, I would love to see like how this would how this plays out with the programs that we bigger BPF projects use. But yeah, super exciting. Thanks a lot for your talk. Thanks. So with that, short 1 minute break, and then we move over to the last talk for the day. All right, so this is the last presentation for today about protocol tracing with eBPF from Omid, Yaxiong, Ryan, John, and Zane. Please kick it off.
Cool. Thanks, Daniel. First thing I wanted to say is we're really so happy to be here. This is our first time at LPC, so it's really, really cool to see the community and all the great work going on. Really awesome stuff, just have to say, all around. And it's so great to just see, I mean, it would have been really nice to see in person people, but it's equally nice just even to see all, all you folks who have contributed so much to eBPF. It's really awesome. So yeah, today I'm going to be talking about protocol tracing with eBPF and what we've done there, and just share some of our experiences. And so before kind of get started, just a little bit about me. So I'm Omid. I was a founding engineer at Pixie Labs, where we started using eBPF to solve observability problems. I'm currently a principal engineer at New Relic. In a former life, I did more stuff with hardware. But these days, working in the observability space. So to kick things off, so a little bit of the history. So we started off in 2019, and our goal was to build a no instrumentation observability platform particularly targeted at Kubernetes, right? Our vision was, let's help developers understand what's happening in their Kubernetes apps. Things that your applications are running on clusters. It's hard to access sometimes. You might not have the right privileges. When something goes wrong, it can be really hard to debug. So what set of tools can we give to application developers out there so that they can better understand their own applications and figure out what's going on when there's an issue, a performance issue, a functional issue, whatever it may be. Right. And so our first goal, our first very specific goal when we set out, was just to trace application network messages. So you have your application in Kubernetes, you have all these different microservices, they're talking to each other. Well, what are they saying to each other, right? And we started off with HTTP, and since then we've expanded out to other protocols. But I mean, it's the basic idea was still like, how can we see what different services are saying to each other? And when building this out, we had two key requirements. The first was that we wanted to be no instrumentation. So we don't want to have people to do code modifications. We don't even want them to have to redeploy their applications. It's really annoying if you have an issue and you have to go modify some code, add some log statement in there, or do something just to be able to get the visibility that you want, or even to redeploy. It's not always practical. So we want it to be zero instrumentation from the user's perspective, right? Essentially, we're doing the instrumentation for them. And then the second thing is we want it to be low overhead, because we wanted to be able to leave this tracing capability on in clusters so that it's always active. You take those two pieces, put them together, and I think everyone in this audience would say, oh yeah, eBPF, right? That's no surprise, right? No instrumentation, kind of just be able to trace things automatically, and then it's super low overhead. Obvious answer is eBPF. So our general approach, which shouldn't be a surprise, but general approach is, we want to capture the data in kernel space with eBPF, take that data and ship it up into user space, where we have a data collector that's part of the Pixie Edge module, which is running on the nodes of your Kubernetes cluster, and that would then take care of, sorting through all the data, parsing it, making sense of it, figuring out that it's HTTP and parsing it appropriately, things like that. And then once it kind of turns that into a structured format, has parsed it out, we would store the data into tables so that we would have the ability to query the data. So part of the Pixie platform is also the power of being able to come as a user and look at historically what's been happening inside your cluster and query it. And so there's a powerful query engine as well and a UI to figure all that stuff out. Run all the queries that you want to run. The focus of this talk, since we're, this is mostly focused on eBPF, is going to be at the bottom end of this stack. So we're going to be talking about what we did with eBPF to actually collect the data and do the protocol parsing and things like that. I wanted to give some context. Like, we'll get into the details, but I just want to give people a taste so they really understand what we're talking about here, is like what the end experience is, because we actually have something working now. So the idea is you can go in through the UI, and we've already traced all the data. We've all traced all the HTTP transactions, and you can just go run a query and say, give me all the HTTP transactions on the cluster for the last 5 minutes, for example. And when you do that, the sort of view that you can get the raw data. You can see the time when a transaction went through, a request went through, the pod that generated the HTTP request, what the other endpoint was, so where was that request going, and then we get full body visibility as well. So it's not just the metadata, but we actually see the contents of the HTTP message as well. So we see, oh, somebody did post to the payment auth, and here's the JSON body inside, here are the headers, here's the response, you see a response that, response 200, so everything was okay, and what was in the body of the response. So we give a wealth of information to the application developers so that they can figure out what's going on in their application. On top of that, then once you have that raw data, it's not too much of a stretch to take that data and turn it into automatic service maps, so you can kind of see who's talking to who within your application, how much bandwidth are they using, if there's any errors on those connections, like are there any HTTP errors, all that sort of stuff we can kind of automatically get once we've collected all this data with eBPF. And then the last kind of contextual slide I have here to just give the big picture is, we also have the ability, because querying is very important for us, we also have this thing called a pixel script, which lets you go sort through the raw data that's been captured with eBPF using a pandas Python-esque query language. So you can do things like filter out if you're looking for only HTTP requests that are going to a particular path, or have an error in them, or had a high latency, or whatever it may be. You can kind of have the full power of a query language to do those sort of filters and kind of get the information that you're trying to get to. So with that context, want to kind of go a level deeper and talk about our experience with building this protocol tracer. So when we set out, again, as we said, we were kind of new to the space. We were kind of saying, okay, so where should we trace the data? There was many options in the software stack, right? So you have the application at the top, but then below that you have essentially the protocol library, like the HTTP library. You may or may not have SSL in your application, and then you get into the Linux kernel where you have essentially your Linux API. You have your syscalls, and socket layer, TCP layer, and the stack goes down all the way down to the network driver. And so we were looking at the different options. We were considering, hey, should we do it with U probes at the library level? Should we do it with K probes at the syscall level? Should we use an approach similar to libpcap, where you're going down lower in the stack? We kind of came from the perspective of we wanted to be as high as possible to the application layer, just because kind of that was the context we were coming from. We were trying to do application performance monitoring, so that's where we're kind of leading towards, but we wanted to evaluate all these options. And so when we looked at all the options, we kind of evaluated them on a number of trade-offs. So we looked at things like, and these are just some of the high-level trade-offs we considered, but like tracing overhead. And I'll show some data on the next slide, but we felt pretty comfortable that with eBPF we'd get fairly low overhead with all these approaches. Another thing that we considered is, so what about the scalability and stability of the eBPF code that we generate? And that's the one where, like, when we started looking at U probes, it quickly became apparent to us that if we try to use U probes to target libraries, it would be a significant development effort, because we need to develop U probes for every library that's out there, which for HTTP is really, there's so much out there that's almost impractical. And even if you do build them, like, how do you make sure, software evolves, right? Libraries evolve. So how do you make sure your probe targets can evolve with the code that exists out there? Now, we'll come back to this later on in the talk, because we end up using U probes for certain things. So that's kind of why I'm hinting at that right now. But clearly, if you go with K probes or a libpcap kind of approach, you have a lot more stability and scalability of writing your eBPF code. And you get those nice same benefits with a libpcap based approach as well. From a parsing effort, it actually turns out that the higher up the stack you go, in some sense, it's easier because you're directly accessing the data that you care about. If you really care about the HTTP request, you're going directly after the source. If you trace at kprobe level, you're getting pretty much the send and receive transactions that are going through, and that doesn't necessarily line up. You're kind of getting the raw data. You have to parse it out. So you need to develop protocol parsers to figure out, make sense of the data that's being sent and received. And then libpcap, it's kind of similar. You have to do a little bit more work in terms of the packet processing as well, because you're getting essentially, packets, not just the protocol layer. And then one last consideration that, again, another one we'll get back to for later on in the talk, but we also were interested in SSL tracing. That's another benefit of doing things at the uprobe level, is that you're actually able to access the clear text if you need to, versus once you're down at the kprobe and libpcap level, the data is all encrypted, and so you can't really make any sense of it. So looking at this landscape, what we decided to do was we thought the right trade-off was to go with kprobes. The uprobes, again, the scalability and stability thing was really the big barrier there. And then between kprobes and libpcap, it was a little bit closer, but we were coming from the perspective of we want to do application performance monitoring, so we thought, hey, let's go for the kprobes. We did do kind of a rough, quick and dirty study to kind of see what the overheads are of these different approaches, or a variety of different approaches. So what we had is, this is a simple HTTP server we deployed. It really does nothing. It just, you send it a request and it'll immediately kind of like send a simple response back. So it doesn't really do any work. And we had it there, and we hit it with as much traffic as we could. So we were trying to hit like peak bandwidth for this HTTP server, right? And then we wanted to say, hey, what happens to this HTTP server once we start probing it? Does its throughput go down? And so we had this set up, we had this jig, and then we started deploying different sorts of probes on it. So we deployed kprobes on the send and receive calls of that server to see what happens to it. And that's the blue line. And what you're looking at in this chart is, so I should explain the chart first. So on the x-axis, what we have is the work per request. So that's saying, like, once the server received a request, did it do any work? Like at the left-hand side, it's really saying it just sends a response immediately. It didn't really have to compute anything, which is not very realistic. Most servers are actually doing something like they have to return some JSON, so they have to go get some data, fetch some stuff, do some computations, maybe access some databases, who knows what. So not very realistic at the left end of it, but it's kind of the extreme point. And as we move over to the right, it's towards more and more realistic applications. And so when we look at, and the y-axis is saying how much performance versus the baseline when it hasn't been probed at all. So how much loss did we get in the throughput of the server just by probing it? And so the blue line that we're looking at is the kprobes, and at the very left-hand side where it was, it's running at peak bandwidth, it doesn't really have any work to do, so it's just like immediately responding. Adding a probe to that, even a kprobe, obviously it's a little bit costly because it interrupts the execution of the program for a little bit, and it's because it's really doing no other work, that becomes noticeable. But quickly, as you start getting the server to do some actual real meaningful work, we see that overhead kind of goes away, and it goes to pretty much zero. We're pretty much the same as if it was not probed at all, so we're running at 100%. To kind of model the libpcap approaches, we tried both TCP and T-Shark, and you kind of get a very similar profile at the low ends. It hurts a little bit, but as you move towards the right, the overheads become less and less. So pretty awesome as well. If you look kind of in the area between on the x-axis between 100 and 200, you kind of see the kprobes are a little bit more efficient. But they're all pretty awesome in our opinion. And then uprobes were take a little bit more of a hit because you're interrupting the execution of the program, and the context has to change and things like that. So it's a little bit more of an overhead there. But our main takeaway from this stuff was that the kprobe overhead can be very, very low. and we weren't too, we were pretty thrilled with that. Like, we could take the K-probes and we felt we could deploy them in real applications. I should also mention this experiment, we are actually doing at least for the K-probe and U-probe, we were actually doing the HTTP parsing as well. So once we captured the data, we did have the prober parsing out the HTTP request to kind of make it realistic. So that kind of validated our approach of going with K-probes, at least from a performance perspective. There's clearly trade-offs. So okay, we decided we wanted to go ahead with K-probe and give that a shot. And so the Pixie data collector, which is codenamed Sterling, so just a little bit of background about that. It's written in C++. Inside the Pixie data collector or Sterling, we use both BCC and BPF trace. So we're super thankful for those projects. We couldn't do it without those. There's the huge community effort on those things is really so awesome. For the protocol tracer in particular, we use BCC because we needed a greater degree of control for all the sorts of different things that we wanted to do with our probes. In other parts of Pixie that are not related to protocol tracing, we actually use BPF trace because that's the better fit. So we kind of, depending on the circumstance, we use both projects. From a requirements perspective, for us, we don't really get to control the target ecosystem because we're developing this for the whole community, and people are on all sorts of different environments. And so we just drew a line in the sand at some point and said, the minimum kernel version that we're going to support is 4.14. Unfortunately, that comes with a whole bunch of restrictions that I'm sure everyone here is aware of. We have the 4,000 instruction limit. That makes us very unhappy, or sad rather. We wish we had more. We don't get to use awesome new features like the ring buffer, which again we would really want to. We've looked into like libbpf and CORE, but that also we can't because we can't control the target ecosystem. It doesn't seem like that's, at least right now, going to work for us, but it may be something that we reevaluate in the future. So let's get into, with the framework and kind of the basics aside, let's talk a little bit about the architecture of how the Sterling or the Pixie data collector works. So we have, so on the left-hand side, what we have is what we're trying to monitor. So we have a target application. It's going to be talking to the Linux kernel. It's going to be performing a whole bunch of different syscalls. And at the high level, what we do is first we set up probes on all the networking related syscalls that we care about. So we're gonna add probes to connect, accept, send, and all the different flavors of send and receive, and so on and so forth. And whenever these syscalls are made by the target application, we're going to trigger and run our BPF probes. And then once our BPF probes run, they're going to extract a whole bunch of information that's relevant from that syscall. Things like we're going to want to know what the PID is. We're also going to want to know what the file descriptor is, because that's essentially, we use the file descriptor to essentially keep track of an entire connection. And the first thing we do is store all this metadata into a BPF map, which we call the connection info map, which is indexed by PID and FD that uniquely identifies the connection for us. Then looking at the data, so whenever there's send and receive, we're processing information in BPF. We have some basic rule-based classification filters. So we're going to look at the traffic a little bit in BPF with very simple rules, and I'll show an example of that a little bit later, to try to see what sort of traffic it is. Is it HTTP traffic? Is it not? And if it meets the traffic class, like if it's a type of protocol that we're actually interested in, if it's going actually, if it's in the address family that we care about, like we'll filter out things like Unix domain sockets, things like that. We'll get rid of all that. But if it's in an address family, like essentially INET or INET6, then we're going to say, okay, this is something interesting, and we actually want to ship this information out into user space. And so we send the information out through 2 perf buffers, one for control events, one for the data, and then it goes out into user space. And then in user space, we have this concept of a connection tracker. The connection tracker keeps all the metadata, and then we have a buffer of all the data, and then we accumulate all that stuff and then start parsing it. and we start parsing the data, according to the protocol into structured messages that we then store in tables for future querying. So that's the basic architecture, and right, it just all works, right? I mean, we didn't run into any problems at all. Everything was smooth sailing, and this is the end of the talk, right? Yeah, of course, no, that's not how things go, right? So, the benefits were we did avoid the complexity of the network layer, and then we did get easy correlation of events to the process ID, so it's very easy to access. You say, okay, this traffic was for this process ID for this file descriptor. But we, for those benefits, we took a whole bunch of different set of challenges. So the first thing that we realized is, dealing with the variety of syscalls that are out there and the way that they get used. And, as we evolved over time, and I'm sure we're not done with these, but we've had bugs where like, oh, something uses a syscall in a slightly different way that we didn't know about, and we're not tracing it properly, right? So that's one set of problems that we're working on. Finding the remote endpoint address. We'd like to extract that information from BPF, but it's not always possible, which I'll get to as well. The implementation of protocol inference in eBPF is another challenge because of the low instruction count and other reasons. And then other things we'll touch on is how we dealt with stateful protocols like HTTP2 and gRPC, and then the question of encrypted traffic. So challenges of tracing the syscalls. So the tracing the syscalls ended up being a double-edged sword for us. The benefit was that it's a super stable API. It made our probes very portable across kernel version. We loved that part of it, obviously. The con is that over the years, many different ways of doing the same thing have evolved, and we don't get to control what applications decide to do. So obviously, we just have to. We're in the observability space, so we have to account for all of them. Today, we trace a total of 17 syscalls to try to figure out what the application is doing, and the list is essentially here. There's a number of connection, kind of what we call connection management sort of syscalls, so things like connect, accept, and close. Then you have receive variants, so things like read and receive message. Analogous ones on the right side, and there's one extra one, send file that is also plays a role. And then we more recently have kind of started going from the syscall layer down into the internals a little bit more. And so we do look occasionally at the socket layer, and so we'll look at sock alloc, sock send message, and sock receive message. More specifically, some of the challenges, some of the interesting cases rather, that we ran into. So the first one is with read and write syscalls. You can use them for both file I/O and sockets. And so because socket traffic could go through these syscalls, we have to probe them. And originally we would end up with a lot more data than we would want to have. And we would try to find different ways of figuring out how to kind of filter this information out. Our latest solution is actually, we now start looking at sock send message and sock receive message on these when we have a read and write. We see if there was a follow-up sock send message or a follow-up sock receive message to know whether that read or write was actually used to send information to the socket or whether it was used for some other purpose, which we don't really care about, and then we filter those out. Another interesting one that we ran into was accept. Accept, you can actually call it with an argument to say, ask the kernel, hey, kernel, populate the remote endpoint address there, and we were using that to actually trace what the remote endpoint was. However, certain applications can choose to leave that argument as null, which is essentially they say, we don't care what the other endpoint is. We're going to accept a connection, but we don't need to currently know what essentially the IP address and port on the other end is. And so that caused an issue for us because we were counting on that in some instances to actually figure out where this communication is talking to with our probes. And so the solution that we've gotten to, at least currently, is we now trace, again, going down a little bit deeper into the socket layer, we trace sock alloc as well as a follow-up to an accept to figure out where the remote endpoint is. so to figure out that information. And then the last example of a challenging case for us is with variants of send and receive that are like things like send message or send M message and receive M message. These are essentially scatter gather send and receives, and we have to loop over the data. The BPF, I mean, we can't have an unbounded loop in BPF, and so we do actually put in a loop that we unroll, but there's only a certain amount of times that we can unroll it within our BPF instruction limit, and so beyond that, at this point right now, we actually just lose the data. Like we can send some metadata saying we lost the data, but we won't be able to get that data beyond a certain number of loops. And we've run into cases where there's been like 30 with some Go applications. There's been these send messages with 30 different buffers in it. So these things do happen. Another challenge that I talked about earlier was how do we resolve the remote endpoint when we were not able to capture it? So, on the previous slide, I said we try to use sock-alloc to get the remote endpoint, but there's also this case where Pixie deploys after the application, right? The application that we're trying to monitor may have been up before we deployed onto the cluster. And there may be long-lived connections, and we start seeing the traffic halfway through. We would have never seen the accept call at the beginning of time, right, or beginning of that connection. And so for this one, we actually have code in user space to try to figure out the remote endpoint. So we have the file descriptor. We do know the file descriptor. We get the inode number of that file descriptor from looking at proc, and then we use netlink to kind of figure out what the remote address for the inode is. It's a little bit tricky actually because it's a little bit more complicated than the picture I have here because file descriptors can get reused. And so when our user space code wakes up and goes and looks at that file descriptor, it might not actually be the right file descriptor that we want to look at. And so we actually have this kind of state machine inside of Sterling that's kind of looking and saying, okay, I'm going to probe this at multiple different times and actually confirm that this is indeed the file descriptor that I actually wanted to find the remote endpoint for, and I'm not mixing up or confusing things there. And this is all just from file descriptors getting reused, and we don't have a unique way of getting the remote address for an old file descriptor. If experts in this community know of a better way, this has been a little bit of a hassle for us. If there's a better way to do it, obviously, we'd love to learn how to do that. So the next just walking through some of the interesting cases or challenges that we've gone through. And the next one is protocol inference. So I said earlier, we don't want to send everything up to user space. We'd like to be able to filter some stuff out that we're just not interested in. And so today we have some eBPF side protocol inference. It's just a filter, so it's okay to have false positives. It's okay to send some stuff up to user space that we shouldn't have. We'll detect that in user space and essentially send a signal back to BPF and say, hey, we weren't interested in that data, and shut that down. But where possible, we'd like to be able to just say, don't even bother sending this up. And so we really just have some basic rule-based code in the BPF, and it's very simple. We'll look at things like when we send or receive, we'll look at the contents, the beginning of the buffer, and we'll say, did it start with HTTP? If it did, that looks like an HTTP response. That's the, every HTTP response starts with that prefix. Or we'll look for, GET, is it a get or a post, or, other commands in the HTTP protocol. So we have started collecting, we start tracing this stuff and have collected a small data set of different traffic patterns. And we do run our BPF inference rules on these different patterns that we have to validate how well these rules are doing. Again, false positives are okay, but we'd like to be able to classify the traffic as well as we can. And so we have a confusion matrix here on the right, which is just saying, if it was MySQL, how many % of the time did we actually classify it as MySQL with the rules that we have? And for simple cases, it actually does pretty well. there are definitely misclassifications, and definitely this data set that we're starting to grow can get a little bit more mature and rich, so we have more examples. But it does, overall, it seems to do pretty well. When it thinks it's Postgres, 98% of the time it gets it right? And so, we're pretty happy with it, although we do face a challenge now with, as we grow the list of protocols, we've been running into more and more cases where these simple rules aren't really scaling as well. It's like, once you especially start getting into binary protocols, they start looking a little bit similar to each other, or the rules are hard to construct in terms of how you infer that some traffic is Kafka, for example. And so we are still actively thinking about this part of like whether we should keep it in BPF or whether there's some other thing that we can do, or whether we have to just start moving this code into user space so that we can do more complicated things. As a follow-on to that, just wanted to point out that we do have, part of the architecture, we have pluggable protocol parsers. So once the eBPF protocol inference says, yes, this looks like traffic that's interesting and we want to trace it, it gets shipped into the connection tracker that I was talking about earlier that holds all the data and metadata. And then based on the protocol that we've classified it as, we'll ship it out to protocol parsers, which will parse it out according to the, we think it's HTTP, we'll parse it out as HTTP, put it in a structured form, and then hold it in a table for future querying. And then, so we're trying to make it easier to have these things be pluggable so that if there's a protocol that we don't support, the community can come in and actually contribute as well and plug in a protocol parser into Pixie and get the visibility into the data that they're interested in. And so we're working on that. Obviously Pixie is open source, so we're trying to include a better contribution guide for how to contribute protocols specifically, so that because we get a lot of requests of like, hey, do you support this protocol? Do you support that protocol? And you can see the list of supported protocols today on the right. There are still protocols that are not yet supported and people are interested in. So that's kind of where we stand with the kind of the basic protocol tracing that we have. So summary, that part was based on kprobes. We were able to grab all the data that we're interested in from the kprobes from the Linux syscalls, and running them through protocol parsers, we can actually get a lot of the data that we're interested in. But there are a few cases that we've run into where kprobes don't work. They're not enough. So this is kind of another level of challenge that we've faced. And so the two examples here are tracing gRPC, which is built on top of HTTP2, and TLS. So let's jump into those. So the problem with gRPC and HTTP2 is that HTTP2 introduced a compression scheme called HPAC. And essentially what HPAC says is, like, let's say you send a request and it has a path that says, in the diagram at the bottom, you can see it says path API get user. The first time it sends that request, it'll actually send the string over, but it will also essentially store that information in a dictionary so that any subsequent times this same string is used, it can send this header, essentially, header string is used, it can actually send just a encoded value for it. And HPAC is more sophisticated. I mean, it does essentially this, but it's a lot more sophisticated and optimized than this. But it's just to kind of demonstrate the idea. And the problem for observability is if we deploy, Pixie deploys, and we start looking at the traffic and we see like, oh, there's a header that has value 87. It's like, well, that doesn't mean anything to us. What do we do with that, right? But it's pretty important for the community if they want to be able to see the transactions within their Kubernetes cluster. The path, for example, is a very important field to know what's actually happening in your application. So we really struggled with this one for a long time, trying to go back and forth and seeing what we want to do with this sort of this case. we thought, hey, maybe we can try to learn the dictionary. We started going that path a little bit and realized quickly that that's way too complex to try to learn it, and we're not going to be able to do it robustly. And there's always a situation where you learn the dictionary, and then we send our data through perf buffers. So what if one event gets lost, and then we've essentially have to relearn the dictionary from there because we may have missed some important information. So that didn't really seem to pan out for us. We thought about, hey, is there any way to recover the dictionary state via the U probes and then keep that state so that we can decode the traffic that we're tracing with our K probes? And studying the code of the gRPC library that we were looking at, it looked pretty complex. And so in the end, what we decided to do is just the best we were able to come up with was, hey, we're just going to trace the gRPC library directly via U probes. So we're not even going to count on K probes in this case. We're just going to go straight to the source to get the data. So, I showed this diagram at the very beginning where we kind of were considering the different points at which we can probe the traffic. And we said we wanted to go with the syscall K probes in most cases, but essentially what we're deciding to do here is we're saying, okay, that actually didn't work for gRPC. And so we're gonna bump it up and go to the HTTP2 library in this case. So we've currently implemented this for Golang's gRPC library, and we have others planned, but it only works on Go gRPC, which also demonstrates one of the problems with doing library U probes is the development effort is obviously kind of an order of magnitude higher because you have to support all the different libraries that may be out there. And I should point out that obviously anything lower than the K probes would also have suffered from the same problem. So we really didn't have a choice there than others to go up. At least what I mean specifically is going down the stack wouldn't have helped, right? So our takeaways from so we ended up doing it. It was a lot of effort. Our experience from it is like what keeps me up a little bit is like, what if we run into another protocol that has stateful information like this? Compression on individual messages is okay. We're not concerned about that. But if there's dependent state within a connection, like the HPAC algorithm does, a message that you've seen before affects how you can decode a previous message. That's kind of an issue for us, or an issue in general for any sort of kind of probing. And so we're always on the lookout for that at this point. Fortunately, all the other protocols that we've had to implement so far haven't run into this problem. And then the UPrib-based approach, we already kind of touched on this, but it is hindered by the scalability problem. So that's the other part that is really annoying, is that we need uprobes for every gRPC library. If that gRPC library changes something, changes the function or the layout of a struct, we have to take care to kind of adapt to that and make things stable across versions. There's some things like if they change the function name, like we're completely restructure the part of the code that we're probing, that's going to be pretty difficult. But if they're just changing structs, we actually wanted, we didn't want to have to hard code anything, and so we wanted to see if there's a way we could make that part more robust. And so what we actually count on to make that part more robust is we actually count on debug symbols. I'll point one out. We'll talk about the debug symbols next, but I just want to point out one other thing. The other interesting one is that Go 1.17 was just released. So in Golang, the new version of Golang, they've actually changed the calling convention, and that's another case where uprobes, the uprobes that we've developed, actually that requires maintenance. So that's just another example of why uprobes are our initial decision to kind of try to stay away from uprobes as much as possible. That kind of validates it because we're learning that things change and uprobes are just very difficult to maintain. Oh, and if there were trace points, obviously we'd use the trace points, but we didn't have access to those. So making uprobes more robust, so what have we got here? So like I said, if a function that we're trying to trace completely gets restructured, we're out of luck. But we said, hey, what if the function is still there, but it's the layout of a particular struct has changed? What can we do to try to make that more robust? And so what we actually do inside of the data collector is that, so let's say, for example, we're tracing this function called write data padded, which is in the HTTP2 library. We're going to deploy a probe to that, and that's going to trigger a BPF program. So first thing we do is we have our BPF program is out there. But we're also going to go, and with Sterling, we're going to go read the debug symbols of that gRPC library. And we're going to take all the dwarf information, and we're actually going to figure out where the offsets of all the interesting fields that we want to read from the function call are laid out. And we're going to take that information, that's step number 3. We're going to essentially, for every PID that we discover that's running this library, we're going to populate a map that says for this process ID, here are the essentially offsets of the different fields in the struct that you're interested in. And so when the BPF program actually gets triggered and runs, it's going to consult that that map, and it's going to say where are the offsets within the different structs and where is everything located, so that our BPF program actually runs correctly for different versions of the gRPC library without breaking. So if the Golang folks change again, they add a field into a struct, our stuff won't break. It'll be robust to that. And this is a short code snippet that kind of just shows, kind of what it looks like. So we have a probe on this write dated padded function. So the first thing we do once we get in here is first we get the TGID, and then we use the TGID to look up this map, which user space should have already populated, that tells us where all the offsets are. And so the arguments, for example, we want to know where stream ID or end stream or the data, where are these things located within, where are they located on the stack, where are different struct offsets, all these sort of information, it's already all there. So we check that that information is there, and if it's only after we've confirmed that we actually have the correct information, that user space has already populated all this stuff, do we continue with the rest of our probe, and we use these configurable offsets coming into the BPF program. Another approach would have been to kind of deploy new, like recompile BPF code, like kind of for every target that we have, to kind of build a new version and kind of compile in, but that just would have been a lot more effort in terms of just every time we have to kind of rerun a compilation, and so we thought this approach worked well for us. SSL tracing. Oh, looks like I'm a little bit running short on time, so I'll go quickly through this.
Yeah.
So
yeah, it's actually 8:02.
Oh, it's 2. Okay.
We'll love for the audience if the opportunity to ask some questions to you. So anyone, if you have questions, comments, feedback, please speak up now.
Hey, thanks for the presentation. I was wondering if you're using any of the information from Pixie for like security, policy enforcement, stuff like this.
Not yet. Today we're focused on just observability, right? But you can imagine that with the query language and everything that we have, like with all the data that we're collecting, you can take that data and then run queries or do the analysis and kind of do sort of analysis of security leaks or affecting policy and things like that. Today, if you look at the open source project that's out there, that's not there. But it's certainly something we've thought about.
Okay, thanks.
So there's a question from Dave. Did you try it with HTTP over quick traffic?
We haven't. Yeah, Quick is one that we're aware of. We have our eye on Quick. It's not something we've gotten to yet. There's going to be certain challenges with Quick, but so we're watching it, and it doesn't seem to be as prevalent. Like I know in certain organizations it's more prevalent. It doesn't seem as prevalent in sort of the general space that we're in, but we're certainly have that on the roadmap for supporting Quick.
So there's a question from Andre. Please speak up. I saw you raised your hand.
Hi, yeah. So on the question of you probing gRPC and like the instability of the interface and all that stuff, have you considered working with like all those gRPC libraries to add USDTs and sort of standardize on USDTs across like different libraries? Then you would have to implement it essentially just once. obviously you would have to discover all that, but like the protocol would be more or less fixed, right? And it's actually extensible over time.
Yeah, that's a fantastic suggestion. And yeah, that is something that, we do want to go ahead and do. There's this catch with us, which is, and unfortunately the Golang community is a little bit more future looking, but there's this catch with us, which is like, we can't, we're a tool for others. So we can't really control what version of Go they use. And sometimes we just have to go to the lowest common denominator, which is really annoying for us because we'd love to be able to just put in USDTs into that code and just use that. And kills all these problems, like you said, that we have with things changing. But because we have to kind of build to the lowest common denominator right now, we have to take on this complexity. But you're absolutely right. Like they should have USDTs in there, and it's something that we should probably invest some time working with them to put those in so that everyone can benefit.
All right, so since we are 5 minutes over time, I'd like to thank you for your talk. It was very interesting. And with that, this concludes our conference day today. And I would still, at the very end, love to thank our sponsors. So basically, Facebook is a diamond sponsor for making all of LPC happen. IBM, Platinum, Gold sponsors ARM and Microsoft. Silver sponsors AWS, Netflix, and Red Hat. Speaker gifts were provided by Collabora and T-shirts VMware, as well as conference services from the Linux Foundation, and again, the LPC Planning Committee. And with that, this concludes our conference day for today. And tomorrow we are back at 7 Pacific time for the last conference day. Thanks everyone, to all the speakers. I think it was really great today, and see you tomorrow. Bye-bye.
you.